Ooh, what?
Something you may not understand in the instructions.
I haven't even seen it. So. Okay.
Here, Ali told me that this is AI, not an L.
Okay.
A lot of people know that.
Okay. Right. So, welcome. Thank you for coming to London. I guess who's going to volunteer themselves for the prize of having come the furthest? Possibly Chris. Anyone further than California? No, never mind. Good. Well, you are the champion already.
Watch the jet lag all day.
Yeah. So it's a great honour, I would say, for Queen Mary and the Centre for Digital Music to host this third web audio conference, and I hope you're going to enjoy it. We've had a pretty good time organising it, and we've been quite relaxed, and I hope that shows through. We don't want to be too stressed or angsty about running a conference here. So I did write a little speech, but most of it, I realised, all the information was on the website. So I'll start with my thanks by pointing you, that's not very helpful, is it, to the committee members. Okay, that's me. So there's one name, two names I really want to point out, which is Yasmina, who's sitting at the front, who's my co-chair, and Sue, who I guess is at the reception desk. You want to turn on the other screen? The trouble is we don't know which one I think it's that one. Okay, great. That's it. That's it. So Yasmina and Sue have really been the driving force to make sure everything happens, to help me, basically. And then we have the programme chairs who just both came up here, Sebastian and Florian, on cue. Matt Parody is helping us with the posters, Matt from the BBC. I think he's our only external member of the committee. The artistic programme, which you'll see some of tonight. Can you read it? Is it a bit small? I don't know how to make it any bigger. The artistic programme has been put together by Giulio. Are you in here, Giulio? No. You'll see him later. He might be going to the venue already, by Giulio and Alo. And then helping with the tech stuff, Alessia, who's also working on the demos and tutorials with Thomas. Thomas, are you here? Thomas has just come in. That's nice. Alessia isn't here, I don't think. Alo, do you want to wave so you get?
Alo is showing the way upstairs.
Oh, right. Okay, he was close by. Ken, who has sorted out the publications, which currently they're on the website, but they will be collected into an online proceedings which will be hosted by Queen Mary's Library. Angela, who's not here with us today, has done the website for us. She's also working on Audio Mostly, which is our sort of companion conference. And by no means least, there's Lynn, who's back there, who's done all the streaming technology, and with fingers crossed, we should be live streaming this now. I don't know. Are we live streaming it now, Lynn? You can't hear me. Is this live streaming now? Already? Probably. I'll just go with a probably. All right. So, also, obviously, I have to thank our sponsors. Our major sponsors are Roly and Yamaha, and thank you to them. And the other sponsors are represented in your bag, which I hope you'd like the logo for. That was designed by Alessia and Thomas. You'll find a little notebook which is from the FAST project, which is another sponsor, and a very helpful pen. Do use them, because I bought a huge number of pens and notebooks for the project, and this is the first chance I've had to get rid of them. So it's very important that we make good use of them. Okay, few details. The lunch arrangements, you've got little vouchers. They are worth £6 in, are all three of those places open that are mentioned on the vouchers, do we know? There's Mucci's, there's the Curve, and then there's, okay, it says Mucci on it as well, so it depends what's open. All of these places to eat are on further across to the east of the campus, not very far, maybe 5 minutes. So you can get a cooked meal, hopefully have a chat. We've got a good long time for lunch. That's today and tomorrow. And then on Wednesday, we're having a joint lunch, sort of more buffet style, in a large space on campus called the Octagon, which is modelled on the British Library Reading Room, which is quite a famous space, some of you may know. So the joint day, Wednesday, we deliberately arranged that audio mostly and the web audio conference would happen the same week here, so that we'd have a sort of week of celebration, and that there's an overlap day. So our program for Wednesday is tutorials. 6 of those, I think, was the last count I noticed. I guess there's some tutorial presenters in the room now, so thank you, folks, for offering to do that. So our program are the tutorials, and they're fascinating, but if you feel a bit more, well, if you feel like leaving the community of the web audio conference, you're welcome to go to the audio mostly, to their keynote. I'm not sure who is the keynote on Wednesday, but you can find that online, and the sessions. So you have a choice, really, on the Wednesday to do either. Okay. Concert arrangements, I think we might mention later. I'll get Allo to say a few words about that. But what I also wanted to do, this is a bit risky, but why not? In the information for attendees, I do suggest you have a look at this. You'll find things about the map of the whole campus here. You'll find information about the lunches, Wi-Fi access. I'm asked to say something about the code in case you're having trouble with that. What I want to point out, if I can find it again, is go to the map for the Trafalgar Tavern. So this is an area called Greenwich. Has anyone been to Greenwich? Perhaps the Londoners have anyway. I haven't been there for a long time, but I was looking at how to get there, and although on the website there's a Docklands Light Railway trip mentioned, if I zoom out, there's this under river foot tunnel, which is quite interesting, really. It's a bit bizarre. I can remember doing it when I was a lot younger, so I'm probably going to try and take the bus. There's a single bus ride, and then you go under the river and would come out a short walk. But if you go earlier, which I would recommend tomorrow for the banquet, there's the Cutty Sark, which is a large T-clipper sailing boat, basically, that's visible there. Is what's that round the world yacht called? Anyone know? There's another small boat there. Any Brits going to help me out with this one? There used to be a small boat there as well that's also quite famous. The Royal Naval College is a beautiful building, and so is the National Maritime Museum, and then there's, oops, that's the wrong way to do it, Greenwich Park, which has got it's not marked here, but the Royal Observatory is there too. So if you can get there a little bit before and spend an hour wandering around, it's a fascinating area of London that possibly you wouldn't normally go to because it's not top of the list of tourist things to do. So I recommend that. Cutty Sark, oh no, I haven't got a note here. Okay. So now to, now to notifications. Poster demo crazes. I've been asked to ask all of those who are participating in the posters to show at there's two of these crazes, which is basically a lightning 1-minute talk for each of you that has a poster or a demo. That'll be at 2 o'clock, and I'm asked to ask you to come along just before 2, quarter to 2, preferably, to run through, make sure with Florian and Sebastian that things are all working. What else do we need to say? Speakers to turn up 15 minutes before their session, please, with the session, and the session chair will be here, plus some volunteers. The Wi-Fi. Okay, the password, if any of you are having any trouble with it, the fourth character is an uppercase I, not a digit 1. Okay? So it's uppercase D, lowercase d, S, I, 2089. Oh, right. Okay. Also in your bag, you'll have found a sheet. We had relatively lengthy discussions about prizes, and in the end we thought we were going to ask the members of the Web Audio API group to get together and recommend us a prize under each of 2 categories. One is for poster or demo, and the other is for presentations. And we'd also like a popular vote, and that's what the sheet's there for. So come 4:30, 5 o'clock tomorrow, if you can fill those in, then between around 5 or 6 o'clock and some point in the middle of the banquet, we'll announce all of the prize winners and give away some t-shirts. I'm afraid that's all we got. You'll have seen a couple of people wearing the t-shirts. Hopefully we'll have your size. And a certificate. Yes, you'll each get a certificate. So we hope, please contribute to that. Try not to photocopy it and vote for yourself hundreds of times, because it look a bit fishy. Just to add a bit of spice to this and reward people who've really worked hard on their presentation. There's a cloakroom. No, hang on. No, there isn't a cloakroom. It says delegates should take care of all their valuable items, as we don't have a cloakroom. Nearly got that wrong. Okay, and the last point before we move on to, you'll need a couple of minutes to make sure it all connects. Is it HDMI?
Depends how you do your audio.
Oh, okay. Lynn will tell us. Yeah. Before we move on to our keynote speaker, the last thing to talk about is health and safety. The fire evacuation assembly point is Geography Square, which I think that's a bit complicated. So what we'll have to try and do is go to the clock tower bit and then find Geography Square from there. There are campus maps, but you're not going to go and look at that when there's a fire. So there's no fire test drills that we know of. So if anything happens, it's a real emergency, and the route would be down the stairs and then left as you come past where you've got your badges, and there's a big green space, and that should be safe enough. I think that's probably all I should really say. So, could I welcome Chris to connect up? So, the question was, Lynn, how are we doing the audio? Would you want it through HDMI preferably?
No, we did our analog.
Okay. Yeah. Analog audio is all right? Lynn? Through... Anyway, while Chris is setting up, I'm not sure really that Chris should need very much introduction. He's been director of Karma at Stanford for as long as I can remember. And we've known each other for a good 20 years, and I think he's got an even older friend in the audience than me. So Chris has been leading one of perhaps the first world-renowned centre in technology and science for music that there was and still is. And the reason I could think of nobody better to invite as our keynote speaker is that Chris has been working on web technologies and audio for probably 2 decades, I guess. Would that be about right? Or maybe I shouldn't interrupt you, but I think that's about right. Certainly I can remember first learning about it at the end of the 90s. So that's getting on for 2 decades ago. So there isn't much he won't know or hasn't seen. And I hope he's going to, I'm sure he's going to show us a few things that we hadn't heard before. And filling in, I think, yeah?
Yep. Audio works.
Yeah, great. I'll get out of the way now. Okay, over to Chris. Thank you, everybody.
Yeah, thanks. Yeah. Okay. Yeah, that's what I was thinking. Yeah, so let me just go over to a sound slide for a sec. Okay. Yeah, good. Okay, so you got a preview. The title points in a couple directions, and this is kind of a privilege for me to point in both directions and take some of your time to talk about things that are on my mind and have been for a couple of years. So first I talk about rhythmic synchronization, and that's like really simple stuff. I mean, that's what we do in music. It's what people love to do in so many aspects of their lives. You synchronize with something, another person, or maybe you're listening to some music and you're synchronized against the beat on the music and it's recorded. What I'm going to distinguish is between 2 types of synchronization. One which is kind of live and interactive, the musician one. The other which is kind of following something fixed, and that's in the simplest case, a metronome, but more likely it's about 99% of what we do these days in music because we're just so tuned into recording. So rhythmic synchronization with a particular focus on interactivity of it. And then this thing, mind's ear, which suggests mind's eye, just a way of saying imagination. And because we're talking about synchronization and music and sound, it's your ability to sort of conjure that in your mind, consciously or unconsciously, mostly unconsciously, but what I'm going to try to do is bring it conscious a little bit in some of the work that's presented today. So here's our friendly native. We have lots of these in California outside my house. They're just a ruckus right now. And these guys are masses of synchronized wing scratchers. That's what they're doing. They're rubbing their wings together in a rhythm, and they're very much responding in a community synchronized fashion. And crickets don't worry about this, probably consciously, but humans have been thinking about this question of the concept of now. Like, when is something going to happen? How do you exist in time as time moves forward in its arrow? You can think of engineering time, which is the reason computers work. We know, down to the femtosecond what we're talking about in terms of now. But in our more organic version of that, is it really the same thing? Is it really this punctual moment? And looking into some of the, paradoxes that have come up in our online jamming stuff, it got more and more interesting to go back to this kind of phenomenology stuff and try to scratch our heads about what is that thing called now that's a blob that's going along, and if you wait for a minute, you're going to really have a hard time figuring out when I clapped versus when a word came through. Like it happened. You can hear that clap. Now you can kind of hear a sort of a remembrance of the clap. It's not a echoic memory anymore. Things are very, very shifty. And how do you look at the shiftiness? Well, turns out here's this time diagram from Husserl 100 years ago that looks a heck of a lot like my attempts to program something that has a span of time and sort of a shifty blob organically moving across time. So we'll kind of go through all of that in this lecture today. But to kind of contextualize it, I'm going to play a video for a little while. This is about 2 years ago, and the idea here was to sell fiber service. This is a Canadian ISP called Telia, and they hired a whole bunch of musicians, spread them out around the country and very unlikely places, and had them play Mozart together. My brother was involved using a jack trip system. It's got, I don't know, like 7 nodes to put this together.
Ja, jag har fått något i knät som jag måste snacka om. De ska på en konsert med dirigenten på konserthuset i Göteborg och 15 musiker utspridda i hela Sverige, och då pratar vi mitt i ingenting för en del av dem. Ja. Hur ska vi lösa det här, tror du? Alltså det låter jättekonstigt om en person spelar pickor och det spelar en grupp.
Jag tror egentligen den stora utmaningen är live, inte hur man fixar det här med utförande av ljud. Alkohol, bil, det är svårt att lämna oro i magen. Men att spela, det handlar ju om att lyssna mycket mer än att titta. Det är det man hör som är avgörande. Det man lyckas med det här med magen, det har man aldrig hänt. Nej.
Even though data travels almost at the speed of light, it still inserts enough delay when you're going over a long distance that just that extra little delay can cause those musicians to not be able to stay in sync. So it's very hard unless you have the right network and the right equipment in place.
You've got a problem on location 4.
Somebody check the latency on that one as soon as possible.
Get the idea, and this is actually one in a whole genre of ISPs trying to sell service by sort of showing people playing music together online. I've got 6 examples. We won't go through all of them, but it's got a good 15-year history, and I don't think it sells a whole lot of extra service. I think it creates a lot of customer service calls. I thought I went full screen, but maybe I didn't. Nope, that's not full screen. I did go full screen. All right, we'll stay there. So back to time diagrams, and this is Husserl a little bit later. The diagram we saw first was kind of a 2D thing, and he started to change it a little more 3D. You know, it's just to say that at that period in philosophy, there was a lot of talk and discussion and new theory about this idea of a kind of floating sense of time. And you know, some things which you know are difficult to understand the first time you read them, at least for me. I'm just going to kind of point to this region of time consciousness and philosophy and say, if you're interested, you can go back and maybe it starts to make sense. Or you can try and program some of these concepts and then get really confused. So that's where we are today in my work. So next in the lineup of advertisements.
From wideband to 4G mobile internet, the fastest next generation internet at home and on the go. Dan! Sorry. Cellular cable, we're moving technology forward to bring you back to the band.
Okay, I still framed that, and there were no wires connecting anything. So we know that you know, it had a different sort of life than the one we're interested in here. But what I did get out of this when I still framed it and started slowing things down and stuff is just a sense of the sort of awesome entrainment, you know, of a musician to a beat. So, you know, you watch the kind of everything that's going on in the physique here, and that part isn't dramatized. That, you know, you'll find that in any musician, you know, when they're sort of in the flow. And it's this kind of flow state that what we're going into, we're going to try to get some empirical read on how tight that is and what some of the complications are in being in this sort of entrainment that's, you know, pretty clearly there. I don't know. You know, if this almost looks medical, but you know, we don't really see it that way when it's happening. You know, the expressions and stuff. Now, these guys, they're also quite periodic. I mean, that's a sense that, you know, between the bugs and the, you know, and the players, that there's all this sort of periodic motor planning going on, which is essential to this concept of flow. And when you're tapping to a metronome, the way I show it here, there's a metronome in blue dots. Those are events, and you can see the flat tempo of them. And then there's a person tapping a key to the same application and recording, you know, the kind of the lead and the lag between those micro timing of the events. And we decided to do this back in about 2004, this kind of analysis of lead and lag, in order to understand something that was kind of crucial to the, you know, online jamming, the stuff that all the ISP hype was about. You know, the idea that musicians might be in different places and be able to synchronize. But when you, you know, and it's very clear that, you know, when things are coupled tightly, as you separate them with small amounts of delay, which is, you know, sort of more often the case than not, then this sort of locking is more difficult. You know, it's fluid. And the question we had back in the time of the experiment I'm showing next is there a breaking point? You know, where is the kind of knee in this temporal separation where things just aren't going to work? And the way we got at it was this experiment that involved a whole bunch of you know, folks that we conscripted at Stanford during a summer project, and we sent them into opposite studios. They couldn't see each other. They just had headphones on and a mic near where they were clapping their hands. And this is what it sounded like. So that's a good run. Didn't sound too off, and we could do it in this room together. It would be very easy to do. But what happens when we separate by kind of drastic distance? These are the delays that we tested. We went from very, very low delay up to 78 milliseconds, and I can sort of frame that in terms of internet transit time on a good next generation network. Stanford to San Diego, for example, is about 9 milliseconds one way. To New York's about 45. 78 would put it out in the kind of mid-Atlantic somewhere on a boat. And so here's what it would sound like between that boat and Stanford. So we actually had to change the experimental protocol because once we got to these extreme delays like that, the partners broke down, and sometimes it was like blame on the other partner that they don't know how to clap. So we just had to preface it with something may go wrong, and that's part of the deal. And now I'm redoing this experiment in a way that it can sort of reach a broader mass to see if I can get data on not just Stanford folks in a studio, but out there in kind of crowd survey land. Mechanical Turk is what I'm using at this point. And this is a run with an adaptive algorithm trying to be clapper A, and then the Mechanical Turk worker being clapper B. And the rhythm here is just straight eighth notes. It's not the really fancy music and the one we did before, but you have to start somewhere. And the really confirming part for this for me about the system is that it blows up exactly the way the one between Stanford and the boat blew up, which is a good thing. This is what it boils down to when you look at that first experiment in terms of lead and lag. You can see how 3 milliseconds, 15 milliseconds, 78 milliseconds really changes the angles of those leads and lags. And we'll think about why that happens. One of the, a particular trial, when it goes through the analysis, looks like this. And what we do is derive those are instantaneous tempo points. That's that sort of zipper-looking exchange between the two clappers back in the studio. And this is a very, very typical looking thing. You saw it in the Mechanical Turk one as well, that there's a kind of anti-phase thing going on between the two collaborating entities when either human or automatic. So there's a way of just sort of picking an average tempo from a diagram like that, and then if we plot all of those, this is back in studio again, we plot all of these across all the groups that we used for trials, and you can see 78 milliseconds in the bottom right. It just shows that there's this deacceleration that's going to be part and parcel to long delays. What was somewhat unexpected was that it's a mouse thing. Look at that. Here at 1 millisecond and even out to the 10 milliseconds, the top row of these, there's actually acceleration going on. And we didn't mention any of this to the subjects. We just said try to keep a steady rhythm. And the acceleration has sort of lots of potential explanations. One thing is that it's very unnatural to have a delay of 1 millisecond between your ear and somebody else's hand clap. So 1 millisecond is about 1 foot in air in terms of transit time. So that's somebody clapping right here. And much more common would be something like 3 meters or whatever. And we found that the more stable sort of separation was kind of this room-sized having a musician 3 meters away. It's pretty natural. And it also indicated that there's probably kind of, almost like in a hardwired sense, some amount of anticipation in the system. So then we can take all of that data and boil it down to one graph, which we did here, and we look for the degradation in tempo as a deacceleration number. Well, actually, it's acceleration here, negative if it's deaccelerating. You can see that around the 15 millisecond delay time, that's where we're hitting about 0, and that would be the steady tempo. And then it drops off. And the answer to our original question, like where's the breakpoint, is that no, there is no breakpoint, at least for people doing this. And it's a very monotonic fit, actually, that you get from this. Then the next step is kind of like, let's do our best job of making a model of one of these clappers to see if we can sort of capture like aspects of anticipation, for example, build that into the model. This was the subject of Juan Pablo Cáceres' thesis at Stanford. And given everything he threw into the research at that point, that red line shows the best job of the model versus the average job of all of those clappers that were recruited. So our model is not as forgiving. And that's where this research is right now. It's like, well, first of all, how do we run lots of tests on a model like that? To manipulate it, get some feedback. That's where the mechanical crowdsourcing comes in, and web audio, because it's essential for this kind of work. Back to our vamping friend here, who is doing something in their head, anticipating, processing what's gone before in a short retention span. Who knows what that is? What's the transfer function of those data points across the recent past? And what we kind of get from looking at this and trying to introspect about it is that what we're looking for thinking in sound. It's part and parcel with thinking in terms of motion as well. But up here, there's something going on that definitely is part of being in this state, where you're entrained and you call it flow. We don't have a word for that. It's kind of missing from the English language. We have lots of image, imagination, imagery, that kind of thing. We don't have really good words for the auditory equivalent of that. Something that's fallen out of use in the language is the description of somebody who's a high-functioning audio imaginer, an audile. So if you're ever accused of being an audile, it's because you're good at this introspection stuff. And I would say that besides planning and our motor planning and sound planning, it's really all locked together with this thinking and time stuff. And the name for this sort of concept, this conscious, this blob we're trying to make conscious about now, how things are moving through, the fact that it doesn't have this super definite point was given a name by William James as the specious present. Actually, he borrowed it from another fellow at the same time. This is the kind of famous quote where we call it that. And it refers to this quandary that we're still kind of getting into. Amazon, 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 Amazon. And I'm kind of zooming through these now, but what we're going to get to is this. And the blue is the perceived sound levels that we were trying to get a handle on. And then the red is the data from this introspective variant of the same thing. And what you'll see is it's, it's shifted, it's compressed, and then we went one more step because we wanted to sort of orient the baselines of both of those. And had a task, again, reading in mind, imagining the sound at that same level, and then going back to the browser and playing a sound to see where that ended up. And that gave a centroid, just shy of the median, and kind of halfway down to the next category. So you can almost imagine doing this, and this is kind of a composition project in the future for me. I'm going to try to synthesize something as if it is from inside your head. Kind of be able to have a dimension of internalness, in some sound work. So we're at present day here, and this is the app which is doing the work on Mechanical Turk now. You can see the interface, which is basically when you start it up, you tap on a control key, and I'd be absolutely honored if people started playing this experiment now. I mean, if you want to go online and just make lots of tapping sounds in the room, you can also do the crickets version. But if you're inclined, go to the page here, and don't be shy. It'll be kind of a nice ruckus to do all the crickets. And you can opt not to and do it later. But anyway, there's the URL. It's pretty simple. It's just off of the Karma site, my account, and then WAC2017. So what you'll find in this set of trials is variations on the time delays, and then also variation on whether the automatic partner that you're tapping against is a metronome, or a fluctuating metronome, or an adaptive model that's kind of trying to do what you do in a sense. And, here's what we get so far. This is the straight metronome in blue, and then the events of a human tapper on the right, and the events by the adaptive algorithm against or collaborating with, let's say, the straight metronome. So you can kind of actually see the behavior of the adaptive algorithm there, but it's got a little bit of history. It overshoots and undershoots, but it kind of stays nearby. Whereas the human, who is me, has been doing this way too long, and I'm pretty good at it. So then, if you go on to Mechanical Turk, you get variation not too different from my own. So here's somebody from literally yesterday that I was able to finagle. Here's the data on the left side. It's both of us humans against the straight metronome. On the right side, it's both of us humans against the sinusoidally fluctuating metronome. And that's a really revealing one to me, because what you see is, and you'll hear it if you run the trial, you'll hear this just about that much fluctuation. And the human performance isn't predicting it, it's lagging. It doesn't know it's coming, and it's adapting. Now, I found an analogy to like, how do we just steer on a road? Have a student who's doing some stuff with cars right now, and that straight road right there, that segment, here are the steering wheel corrections that are going on as going down the straight road. So think of the straight road as a metronome. And to stay on it, you're always kind of like coming back. You can't just hold it. And I haven't seen any data that's like metronome on top of metronome that comes from a human. And however, when you're in the curve, and this is stuff that we don't really know the answers to right now, but when you're in the curve, either on the road or following that sinusoid, if you see it coming, you're going to go with it. You don't micro-correct nearly as much. You're kind of on the curve really easily. And when you come back to straight, that's when you start seeing this even sometimes quite periodic correction going on. Here's what two adaptive tappers do when they're coupled together now. And this is graduated across delays. So you can see exactly what we had in the experiment with the humans. We did massive trials here. In individual trials, you're getting acceleration at 0, kind of in whatever 6 milliseconds is in this mechanical torque system. I'm not sure what the total round trip is yet, because there's a lot of operating system and other kind of stuff going on. I haven't measured it. But for my part, the amount of delay I had to put into the code to hold a rhythm was around 6 milliseconds. And you get degradation there. And then same setup, but now we replace a human into the pair, and it sort of behaves in the same way. And then if you go out to 78 milliseconds, I just plugged in that number from Stanford to the boat, and it just dropped off precipitously like this. And it actually comes down to a kind of evens out at a very slow tempo. And this has been noted in some of the papers that are in this area now, that it never just keeps going off a cliff unless it's something to do with code, which happens in my code. But, here's what I programmed as far as an algorithm. It's very simple recursion that comes up when you hook a blue algorithm to a red algorithm. It's basically, I'm waiting for you, you're waiting for me, but we both have sort of a bit of a flywheel to predict where we're going to be. And when we look at improvements to that, it's got to have something to do with what's in this sort of mystery circle here, where how do we integrate previous events into a prediction for the future? And I think I now have like something I can share in terms of a platform for working on that. I don't have the answers for it, but I'd love to, first thing, not have just a pure sum of a fixed, like a leaky integrator across the back, do something with more elaborate transfer function and stuff like that might help it. And just to remind you that, this is what this role is imagining. It goes through forwarding events here. It's looking at past events and modifying them. So it's the C star, the C star star. Those are evolving memories of some past event. And then just to wrap up where we are now, we have a group doing some piano coupled stuff where they're manipulating time delay between the two performers, and they're doing not just clap rhythms, but now they're putting some pitch contour on it, which helps make it come a little closer to the musical, showing a lot of the same tempo degradation. So the different colors are showing you 10 millisecond, 20 millisecond, 40 millisecond. And then just a moment about what this is built out of right now. It's what I had available, and I'm here to learn from all of you. It's going to be a pleasure if anybody has comments to help me get this better. If I do my work in another language like Chuck, where I can be absolutely sample synchronous and completely predictable about concurrent programming, so when I push off a thread. I know exactly what's happening at what time, get it back. When I'm writing this in something using the promises and the async, await pair, I'm getting good service, but I don't have that sample accurate confidence about what's going on in the machine yet. And we'd love to know more about that. It's been an absolute joy and pleasure working with Faust to generate the ESP for this. So like the tapper that you'll hear has slight variations from one tap to the next, so that it doesn't just sound like a machine. All of that's coded in Faust and very easily incorporated, but it does create a requirement of being in the script processor mode, which is fine so far, but I'd love to get the timing better. And with that, I'm just going to point out that this is the work of a large number of people helping out, and we sort of all understand bits and pieces, and I'd like to thank them and the ones that I forgot as well at this point. I would like to close there and say thank you for your attention.
So I was interested in the amount in which people were projecting as opposed to reacting to previously heard sounds for the rhythm thing. I wondered if you considered an experiment where two parties continue and told me at any point one of them might stop and they have to do their own part for a while, and how rapidly that falls off and how that relates to the life that they had previously.
Thank you. It's not been done, and it's a great idea. It's very, very easy to implement now, and I'm pretty curious. Yeah, just coming back to it and get it. Thank you. Yeah.
Yes, there's also a lot of research in terms of how visual information plays into time perception and synchronization. So I'm wondering what kind of effects do you think you would see in doing this research in terms of if you were to allow collaboration to see one another?
Great. We've done some seat of the pants work on that. There's nothing publishable at all, and it's something I haven't. I've seen one other paper on so far. So you're mentioning a very fruitful area that again hasn't had enough attention. I think but when I was doing the seat of the pants thing, I just have to mention one thing that was very peculiar was we were looking at how do you get people to start together, right? And if you're visually connected, you can cue, and that's what we do in places where we have speed of light or image travel. Not on the network. It's always slower than the audio that we're doing. The uncompressed audio goes across really fast, and then here comes the action a little bit later, right? So found some sort of ironic stuff going on. It almost seemed like parapsychology. I'm going to say somebody should do this.
Yes, I've got a question, because I'm no expert in this area, but as a musician, I'm aware of conductors who have the ability in extremely complicated contemporary scores, where you are not only changing time signature each bar, but also the tempo is changing. Some conductors have an ability to actually let the musicians know what the next tempo is going to be. And that is through the visual movement, the physical movement. And I wonder how much that relates to this.
Right. And so that's such a super tuned, context that we're talking about, where you warn your conductor has an absolutely precise way to conjure that in the moment. It's not playback from video. It's this is something that's responding to the musicians as well as them responding to it. So it's another kind of coupled phenomenon like that. I can't comment too much except to say that I know this as well from a kind of musician point of view, and it's absolutely uncanny. this kind of sense of time that we all have and can exploit in music. One of the exercises I do with my incoming class is to play, and I guess this is incoming in a couple weeks, and we'll do it again. Play little 100 millisecond clips at the beginning of kind of well-known anything. It could be Rite of Spring, it could be something. So I just play a sound, and then another one, and ask them to identify, well, can you at least pick out your genre, or maybe the instrument, or something like that. It's another one of these uncanny things because they're nailing it sometimes. They'll tell you exactly which Santana piece. I've been just really thrilled to see people say Rite of Spring. I mean, the same thing, just from, which was longer than 100 milliseconds. 100 milliseconds is the time from just about this wall to that wall and back. I mean, it's really short. So, what to say about that, though, is that how would you get the tempo from? So, up tempo, Michael Breckerton, as part of my arsenal for this test, is it just starts with, and they say, okay, now everybody start nodding to the tempo. I think, they've already figured out it's jazz, but that's pretty quick. And then a ballad comes in. And this is like, and everybody's doing this after hearing. So where's that come from? I think we just have a wonderful kind of identity capture mechanism that's working for us all the time, and it's describing musical, interesting things, and, stuff like that. So.
We have time for one more question. And I'm sort of going to ask you to give your name. I forgot to ask anyone else, but if you could just say who you are, where you're from, it's nice to know.
Yeah, so I guess it depends on the situation. Like, if it's accelerating in a rock concert where they're with the musicians and the whole thing is starting to move, that can be a kind of consensual act, between whoever's the powerhouse for the rhythm. If they're clapping along with, something like that. If you split it up differently so that the group of untrained people clapping are meant to be holding time, it may not actually happen. So there's different things that influence that that path of acceleration. And sometimes large groups slow down also, which is some sort of massive choir kinds of things they just sing. Like that. And in a delightful way, Pauline Oliveros had this piece that was done with 7,000 people in Central Park in New York. It was a meditation. And it wanted to slam.
Well, that's great. Thank you very much, Chris, for getting this. Come for some pretty great start.
Thanks for inviting me.
We've been a lot, there's some coffee and tea and other things, I remember, outside. In the meantime, we're trying to figure out how to switch this on so that we can capture questions and answers for the stream. Correct, see you in half an hour.
Chris, you're, I think we've met.
What about this? Will it go off then? Yeah, it was very nice.
Yeah, I'm just,
I found the switch.
Great presentation.
Test, okay.
Okay, maybe.
Maybe I should apply from
So if I try with, do we have a way to hear you? No, probably not, right?
Well, yeah, when you connected, I should be able to see it.
Okay. I'm going to try to connect to HDMI.
Yes.
Es war die ganze Zeit so ein Brummen drauf, aber ich dachte, irgendwie kommt vielleicht hier falsch.
Ja, das könnte schon sein. Also ich müsste mal hören. Obwohl, jetzt hat er wahrscheinlich den Raum.
Sag doch mal was. Achso. Okay. So does anything change in terms blah blah test level test? Rauschen geht runter. Also der Broom ist natürlich schon noch da, aber zumindest. Okay. Ja, viel besser. Okay. Muss man einfach müssen wir das anschließen? Und dann Audio vom Computer. Soll ich mal alles abspielen? Dadurch? Oder haben die das verwendet? Ja, er gerade hat das verwendet. Aber dann müssen wir hier. Kann ich mal da. Obwohl, jetzt mache ich fast ein Feedback. Aber da kann ich natürlich nicht. Kann ich natürlich nicht hören, jetzt was passiert. Also mit dem Delay ja. Achso, das tun ist, man kann jetzt hier wir müssen es mal einschalten. Ist halt da auch. I'm connected to the HDMI now. I didn't even check that. We checked the audio, so people will have to.
Expert on settings.
Monitor is connected to this machine. Monitor is connected to this machine.
This one. So projector 1, 2,
something like this, yeah.
Okay.
I think that is.
Yeah, he landed well.
It's fine. It's just the second screen, but.
Yeah. Yeah.
I think it is recording.
No.
Yeah, I think it should.
Ah, there is still this image saved in the live stream. It still marks image somehow.
Can you refresh it?
Yeah, it is. It's live. But this is just not. This is out of date.
Yeah, it wasn't that stuff. Yeah,
oh, we have 3. Yeah. I don't know. Why did it always come to this?
Yeah. It seems stuck on this image from Mark.
I mean, that is still probably from studio.
Yeah.
No. Yeah.
So it's just recording the PC.
Okay.
So probably if I close this.
Ah, it's the PC he was using.
But you recorded
the wrong one
somehow as well, right?
Yeah.
Can you record a laptop? So we have to switch source here. Yeah, but and it was here on the monitor now.
I will try it again.
Oh, and now you maybe have to switch something else there, or do you?
Yeah.
Because this is now on the computer here.
Okay, I will try to record it to see if you want to.
Yeah. Oh.
Yeah, that is, it's just recording whatever, independent of what we select here. It's always recording the PC because it's, you know, here. It's this.
Oh, yeah, yeah. Hmm. Ja, eben genau. Aber auch wenn sie dann Pause lassen, dann geht es aber oben kann man vielleicht auch umstellen. Jetzt ist sie gestoppt. Oh nein. Also das geht. Aha, nee, das geht auch, wenn du auf VGA schaltest. Aber dann kann mit VGA geht es wahrscheinlich dann der Livestream nicht mehr. Mit HDMI. Jetzt sieht es ganz aus, ne? Jetzt sieht es auch höher. Oh, jetzt hat er das wieder gekriegt. Jetzt habe ich den. Ich gehe mal schauen. Keine Ahnung. Ich guck mal, wo der.
Yes, we are. Yeah. I need to double check that. That's good. I better make sure that my talking makes sense. Are you? We still, yeah. I mean, there are live streams. Yeah. Okay, yes, I forgot that Joe's been a quick lot longer than I think. That's right, that's great.
Are you based in London now?
No, I'm still in the office. I'm just going to do 1 minute to start proving my email.
People keep telling me to go and have tea, and that's a very good idea.
Okay, I'll see you there in a second.
Okay.
Good to meet you. I'll see you again.
we're trying to build aesthetics or virtual reality, or right now we're really focusing on assistive technology for people who have strokes. So people who can't understand that they have illnesses that they have, because that was possibly used for that. So our technology used to help those people. Yeah, it's been a real easy. Definitely not my favorite. Definitely not. Yeah, it's definitely good skill to have. I'm kind of jaded from those, so I think that's when it's I'm less. Yeah, it's going. Good. Like, if I had any inclination that academia wasn't my thing, then it's all coming. It's hard just always thinking about money like that. I just kind of stressed out. It's not really digital private decisions that new, where it's like I do more of my stuff. How available it is, how cool, you know, how different.
Exactly. I guess we have access. Hey.
How's it going?
Yeah, how are you?
Fine.
Looking forward to your talk.
Me too.
You would check stages?
Absolutely. Cool. No one should ever look forward to their own talk.
That's right.
Hi.
Hey.
How are you? We still have some issues with the stream. And so we have to figure out how we can actually get VGA signal to the stream.
I see. Well, I will let
you use
solve
HDMI
that.
or
as you like,
yeah,
whatever.
I think would be
it might crash my machine, but I.
Yeah,
Shall we try it?
Sure. Yeah. Let's try.
I'm a little bit nervous about HDMI. I had some weird experiences.
Yeah, and then with audio, usually it's also not. I'm not sure.
But you see, my dock doesn't work anymore. You know, that's the weird thing about it. And then we just go kill.
Also the screen
minus kill. You know, and or kill all. And when we kill the dock, I think. What about the finder, maybe too? Eventually. And then it goes. And that's it. Great. And then I will try to make some sound. Oh, this doesn't, this talk has sound. This like, there's no.
Yeah, there's, not sure if it's because this is not. Okay, maybe we can try with this. So now, I don't know if it's difficult. I don't. Well, Lynn can probably help us. How to get the audio signal while we have HDMI?
Maybe I must do something. Maybe no.
It's possible.
Maybe I must do something.
So we have to.
Look at this. Built-in audio output is.
Okay.
No. It is selected already. I think. I think we are fine on this side, honestly.
Yeah, I think so too. It's whenever we use HDMI, this system actually thinks the audio will come from HDMI.
Now you are using VGA or
HDMI.
And do we have an alternative? We
have to have an alternative. I guess, do we have an adapter?
I have an adapter.
adapter to
to Mac.
So we go for VGA, no?
I think it would
Sounds-
probably be safer, yeah.
Sounds like a
But then we have to see if
viable
the live
solution.
Actually,
For me,
you
at
need
least.
the audio.
the audio while using HDMI doesn't work, I guess. Do you?
Yeah, that's
we already
normal.
can
You have
try
to
it
switch
if
to
it works.
VGA. Unless you switch to HDMI audio.
We
in your
can try it
settings.
this way.
Yeah.
Right, we can try it this way.
Even though then
put-
it's maybe too complicated for
For?
every speaker will have to do exactly that. I don't know.
Maybe we use
There we go. And so let's try it this way around.
I think a lot of people would want to use their
Now.
own.
HDMI audio. You need play audio from the loudspeaker.
Technology, isn't it great?
I must kill the duck.
So, but now that we're using, if we try to use VGA, it will probably
See that?
Oh, yes, yes. We can. Do we have adapter? We have adapter.
I guess no, we don't have our
okay.
own adapter.
Oh, maybe.
So I will try it once more with this, and we do it the other way around. Then I will.
So it would have to. Are we going? One more.
Okay, do it just the other way around. Aha. But now again, I must go for killing the duck. Okay. Here we are back, and then what I wanted to do was to go for the HDMI as default. Use this device for sound output, and then we go back here and start this. Okay.
Okay.
Now there is sound.
If you switch, so you switch sound source?
Yeah. Now the last time we tried with this.
Yeah, that is, yeah.
I don't have a control anymore on sound.
Oh. Yeah, so.
Is this all we get? I mean, it's not that.
Yeah, on VGA, so I think the jack output is a bit louder. If it's a problem, then we should probably use
But
that.
the jack output.
Yeah, but then we
So
have to
let's
use
try.
VGA
Let's try now
output
VGA and jack output.
VGA and jack.
Jack
I like
trip
VGA.
jack?
No, just mini jack.
Ah, okay. Hey, so if I do the math and divide, everyone has 20 minutes total. Should I tell them they have until 15 minutes and then leave some questions?
Yeah, or ideally, I guess. Yeah. Otherwise,
Let's
you
say
just
17.
lose question time.
Well, if I aim for 15, they'll keep talking for another 2.
Yeah.
No, 15.
Or like we don't know
Well, someone.
We will maybe win some time right away. I think I will be done in 12 minutes.
It's such a high that there was no
yeah, we found we can offer, but it doesn't. Even though that's actually the.
What, do you need this?
I'm not sure.
No,
it's the Wi-Fi?
here. No, it's
Oh,
not.
that was here.
It was here.
Oh, come on.
So now all we need to figure out is how to get the
You want to try too if it works for you, right? I'm sorry, but I'm not done yet.
Because I'm nervous
here.
after seeing that.
Yeah.
That's why 15
The only
minutes
thing
is
you have to
probably
know
better
is
than we have
that
longer time to
jack
switch.
output only works when you select VGA
Liam,
there.
we're using VGA now. Do you get the signal?
Okay.
Oh, HDMI to VGA. No, probably rather the opposite.
You want
no, it's fine. We just use it.
This is really not sane. Try yours and then. I mean, VGA should just work.
Then the audio jack is
there we
right
go.
here. Is this? Yes.
Shit. Oh. This is not good.
How visible is that?
Doesn't look very professional, though.
I'm sorry.
It's not very wet either.
I should send something and a push notification to a website that
Yes.
shows up on their laptop.
Okay, now this is not coming on my computer.
The sound?
The sound is dead. Which may be an issue with my jack.
Oh, you think so? But
Yeah.
you can use, well, you're using VGA
Mm-hmm.
as opposed to AC.
Yeah.
You should come through that way. You got it?
I can do the HDMI way, so if I know how to change it quick, it's just I would take
Oh, yeah.
this
It's,
because I'm pretty sure my jack is faulty, and I don't need super loud audio. Oh, except for I don't have a adapter.
oh, look, this is it. It's good that you're instead of pressing that one, you just tap that.
Oh, but no, there's, jeez, because, yeah, I have an adapter, but not for, I do not have an adapter. I thought I did.
Is something working now?
That's a great question.
I just erased that of my part, but everything's okay apart from that. So here we have it back. So I will now connect the VGA. Where's the VGA now? Thank you.
Could I possibly forward my presentation to you and present on your laptop? If that's a possibility.
If you don't want to do this now,
yeah,
everything is okay. You can do with my laptop.
Yeah, so I have
whatever
a faulty
you
jack
want.
that doesn't work sometimes. It's an indeterminate jack. And I know that's an issue. It happens.
Sarcastic output.
Yes. So I have a Google slide, so as long as someone's willing to let me sign on real quick before my presentation, it should be fine.
I will reboot my machine, and I think it will be okay.
Yeah. So VGA is.
Yes, you're first, I'm third, so if we'll just leave this up here, I'll just sign in, if that's cool.
Do you have a USB stick or something? Achso, machen wir das auf Deutsch, oder?
Ja.
Thank you. Take it away.
Thank you. So I'm presenting here the work of David Keynote, my colleague at IRCAM. I'm Norbert Schnell. And it's about using spectators' smartphones as a distributed network of speakers and sensors during live performances called New Soundworks. And we could say, okay, it's actually, you know, distributed mobile web audio for cycling Ableton Max users. So if you don't know Max and you don't care about Max, this is not for you. And actually, I was using myself Max for 20 years, and I gave up using it around 3 years ago. So it's a kind of irony that I'm here today in the morning and open the conference with this talk. Thanks, David. And I said to David, don't do that. You know, we were working on this project together, and I was happy to get rid of Maximus P, and he started to drag this back into Maximus P. I said, David, don't do that, don't do that. But he didn't listen, so we're here. I'm giving this presentation this morning. So, of course, IRCAM is a place where everybody literally uses Maximus P all day long. So, of course, it made sense. After working 3-4 years in this wonderful research project where we explored everything you can do with web technologies and mobile technologies, with audiences, improvising, participating in concerts, in installations. I will talk large and long tomorrow about this project in a talk. Cosima, so what I'm presenting now, the New Soundworks, has been done in this framework. One thing we did in the framework of the Cosima project was to develop a framework that is basically the code that we, from one experience we implemented to another, our tests, our pilot projects, our prototypes we developed from one to the other. There was always this bit of code that was the same from one to the other, and we collected these pieces of code, and that is basically Soundworks. So it's not a big deal, it's a pure HTML5 JavaScript plus Node.js framework with some hopefully helpful set of services like clock synchronization for the clients and audio event scheduling, a metric scheduler, for example, shared configuration and parameters that you can control parameters from everywhere, and so on, a file loader that is pretty kind of handy, and things like this, predefined views that easily you can make interfaces, but it's all JavaScript, of course. And, well, of course, that is not something you can hit all these people with who, or excite people with who think that they really don't want to program. You know, there are these people who are programming whole day long with graphical interfaces, but they don't believe that they are programming, and they don't want to believe that they are programming, and they certainly don't want to open a text editor and write code into a text editor. And for these people, of course, David had this brilliant idea to drag everything we did in HTML5 JavaScript Node over to Maximus P. So it's obvious, I mean, I don't have to talk at the WAC about the advantages of using web technologies. Is there anybody who doesn't know anything about Maximus P? I'm sure there are people who never heard about Maximus P here, no? Yeah, I'm happy. Welcome. So, of course, it has a graphical user interface, and it's a graphical programming. It's simple to do graphical user interfaces. With this graphical user interface, it has many powerful modules, and it's very known in a certain community of composers, and here are close to VST and Ableton Live and things. But, you know, it's no web, and there's a little bit of web. There's quite a lot of web, to be honest. They did a great job to drag lots of web stuff into Maximus P over the last years, by the way. And, but it's certainly not running on mobile phones. Oh, this should be actually not a green thing, but a red thing down there. This is the disadvantages on the last line. Sorry, David, I messed it up. So this was the motivation. So the concept is that it is a collection of single-minded modules that do sound synthesis or visuals or sensors, tapping into the sensors on the mobile phones, and everything runs in this Soundworks Node.js HTML5 framework client server. And there is a max proxy for each of these collection of modules. And I will give you an idea of what these modules do. So there's a max proxy. You program everything. You set up and control everything from MaxMSP, even though it is totally web and audio. So this is this bad idea David had. And so here's an example. So what we see here is on the left side, MaxMSP, or Max, Cycling Ableton Max. And you see a little graphical interface where you have a representation of a grid of mobile devices and a ball that you can move around to move sound over these mobile devices. And on the right side, you see a screenshot of a computer screen with 12 instances of Chrome simulating mobile devices. And so this is a typical situation where you would set up your mobile experience, imagining there will be people in the audience, and use MaxMSP to control what's happening on the devices. This is the general architecture of the thing. So here's the Max part of it that would over OSC talk to a Node.js server, and then from there to the clients. And here everything is OSC, and of course here everything is WebSocket. So this is the part you would worry about after having started your Node.js server. This is the thing you worry about as a programmer and user of this thing, and the rest is just for free in the background. This is kind of the modules David came up with. So groups is what I just explained, that you move around and sound would move over the peoples depending on their predefined position. And loop is a sequencer. Then there's a room reverb simulation that this matrix or this distribution of mobile phones with determined positions would act like a room reverb simulator, which sounds funny. There will be a little video I will show you. And then there's a module where you could draw paths in MaxMSP, and sounds would rush over these smartphone distribution in a certain order. And well, there's some synthesis, some granular synthesis. You can stream sound from MaxMSP to the mobile devices, and you can get the sensor orientation and motion data sensor from the devices in MaxMSP with a tag and all this and all this. And you can do some text. You can text from MaxMSP on the mobile devices and display images and level meters and things like that. Here's a little video, because I want to do a demo of this. This room reverb simulation with a reduced sound speed. This is the path I told you about. This is David hiding behind a dummy head. This is this loop sequencer where you can do sequences over the different. And this is the one device controlling energy on the other devices. So David came up with this really brilliant idea that when you simulate your mobile devices with a browser, you have as many instances, of course, as you like using Chrome on a machine. He would kind of insert this module to it that is binaural spatialization. Of course, they add all to the stereo output of the machine, but they could be located then at their position, and you would have a kind of binaural simulation of how it could sound, or having all these devices together. Yeah, and I think this is pretty much what I wanted to show you today. And all this is under BSD3 on GitHub. And honestly, the paper is not the last state of the thing. There's a list of devices, there's a documentation, a full documentation on GitHub of this. And well, thanks, David. Fuck you. And thank you very much. Are there any questions?
That was so on time. Yes.
I should follow my own rule. Mark sounded very merry. Is the idea that these devices would actually be held by people in a space, or that they would be on so normally they'd be moving?
Sorry, I didn't insist very much on this because it's kind of a WAC thing after all, right? That we have all these contributions where all this is done, if that was not clear, all this is done for the context of doing, let's say, participative concerts and collective improvisations with an audience of people pulling their smartphone out of the pocket and spontaneously joining others to make music.
How would you get the position of the individual smartphones?
So we implemented in Soundworks a couple of them possibilities that are available in NU. That is basically always asking the people where they are or determining them from a theater ticket or things like that. There's no fancy stuff.
So in the videos that you showed us, like it was, I think, if I understood correctly, all the devices were the same manufacturer. Is there any challenges around compensating for different device types if in a real world scenario, for example, you would have different devices of different manufacturers?
That's terrible, and that won't be solved before the next standard of web audio is implemented in the browsers.
You showed a nice example of one device controlling many other devices, but is it possible that any of these devices is a controller too? And if so, because it's a twofold question, what would be the scalability of the virtual instrument that is controlled by a varying number of people?
Salut Vincent.
Salut Norbert.
Nice to see you. So, two questions. First is, yes, definitely you can get the streams, sensor streams of all devices. You can switch them on and off individually from MaxMSP and get all of them. And do in MaxMSP, they're all streamed through MaxMSP, and then wherever you like, with a route, and you send them back via your OSC to the server, and the server sends it back. So, of course, you're putting your finger on the scalability issue that is certainly huge. We don't know where it starts and where it ends. We did tests, with tens of devices, 20, 30, 50, but it ends certainly suddenly somewhere, but we don't know where exactly. But the scalability is an issue that is enormous in this thing. But to defend David and his work, it's really for prototyping such things, and I'm sure for audiences with 100 people or 150 people, typical MaxMSP concert audiences, I think it will do.
So in the video, the bass response was really good. How was that possible?
Yeah, good point. You mean there weren't any mobile loudspeakers connected to the mobile? No, it's a simulation. He redid it once more with his wonderful idea of binaural, because good question thing. I should have said that. I should have said that right away. I don't like things like that. Of course, now it's a simulation, and he redid the same scenarios with the simulation after figuring out that it sounds actually not so bad in the room, but picked up by a dummy head, which is 2 meters or 1.5 meters above, and listening from down, it was horrible.
Okay, can we thank the speaker for? And where is Gerard? And I want to give a special thanks because you took us with your very succinct talk. You took us from 5 minutes behind to being exactly on time. So thank you.
Yeah, this is good. There's no audio, unfortunately.
And our next speaker is Gerard Roma from Georgia Tech University to talk to us about loop-aware audio recording for the web.
Right, so this is by the way, collaboration with Anna Chambaud and Jason Freeman. And it's sort of a proposal of a use case for web audio, the idea of facilitating the process of capturing loops in kind of casual situations. So I think probably it makes no sense to try to explain what's a music loop in this conference. I mean, certainly everyone knows what is a music loop, but I think it's maybe fair to emphasize a bit the importance of music loops historically as the role in the democratization of music production, right? So since the first usage of Kai's samplers, such as the MPC in hip hop, up to current interfaces like the GarageBand for iPad. The music loops are usually seen as perhaps the easiest way to produce electronic music. And this both from the point of view of music theory, where you don't need a lot of music theory background, and from the point of view of the technology, where it's actually, it leads itself to very simple interfaces. And of course, part of the reason it's so easy is because somebody has done part of the work for you, right? So here, I would like to focus a bit more on this part, which is often overlooked, like the process of who creates a loop and how it's created. And so, of course, now the web is a platform for sharing loops, and there are plenty of websites you can use for getting loops. Some of them will, I think, emphasize a bit more the role of the person who uploads the loop. And so, in this sense, there is the question whether we can shift a bit the perspective towards seeing this as a collaboration. So traditionally, it was either you stealing something, or some professional has created a loop and it's an anonymous professional. But maybe we can see this as a collaboration between the person who created the loop and the people who use the loop. And so one good example of a web application using loops is Sketch. This is the research context where this work has originated. And it's an application for, basically it's oriented to create, to learning computer science in high schools using music composition, digital audio workstation. And it's all based on loops. And so it's, I think, quite interesting part of it is that there's a time stretch algorithm so that you choose a tempo, and there's a library of only like 4,000 loops, but all of them can match your tempo thanks to the time stretch. So it's an example of using a loop database, relatively small, for a complete application, and there's like about 8,000 compositions that they have done using this. So I think it's a nice example, but so again, it follows kind of the traditional approach where you have a database of loops that has been commissioned to two composers, two sound designers, and there is an interface for recording loops, but most people don't use it. Sorry. And so the reason that people won't use it is because it's not difficult to create a loop, but it's sort of a bit laborious. And this applies to the interfaces that most people will use. So generally, either you use a digital audio workstation, and then, so by the way, I envision this as a kind of process where you are kind of exploring musical ideas with an instrument or some device, and then you want to record a loop. And then you have to stop, because in the workstation you have to like define the tempo, you define the meter, and in this case, if you want the loop to be recorded like automatically, then you would need to use a metronome sound, which is sort of annoying. And you have to make sure that the metronome sound doesn't get into the microphone and stuff like that. And of course, the other alternative is to just record what you're doing and then spend some time editing the loop start and end points, and making sure it plays well. So here what I'm proposing is to automate this so that you don't need neither the digital audio workstation interface nor the loop editing task, and you can kind of capture loops in a more like casual way. Of course, a more dedicated musician that plays with loops often may have something like a loop pedal to capture loops. But for web audio, for web applications, this idea of automating the loop recording, I think it would make a lot of sense. So the idea of automatically detecting the loop has been in the musical information retrieval field for quite a long time. Ever since in 2001, Jonathan Foote published a couple of papers about the beat spectrum, and then similar ideas based on the self-similarity matrices have been used in MIR. I think the main applications that I know of is either you take some song and find the most repeated part of it to use it as a thumbnail, so there's the song that you would listen to when you're browsing a database. Or there was also some research about finding the most repeated part of a song as a loop for new compositions as well. And then 2 years ago in Web Audio Conference, we proposed an application of this algorithm as well to analyzing, so indexing unstructured databases, meaning we working on free sound, we proposed this algorithm as a way to consistently index sounds that are not consistently labeled as loops, or not always. So in this case, the difference is we're proposing a JavaScript implementation that is to be used for recording. And here, there's a bit of a difference case. And so the tasks that we identified are, well, the loop period estimation. This is something that the loop spectrum gives you kind of very easily. But then you have to find where the loop starts in a kind of background, potentially noisy background. And then there would be a task of candidate selection. So when you repeat something several times, you have, of course, several copies, and you have to select the one that is the most, that suits most. And we did 2 experiments for the first 2 of these tasks that I'm going to describe very briefly. I'm not sure you can see this very well, but to summarize the algorithm very quickly, so we do some analysis over on a short time Fourier transform, and then from here you compute some sort of features, and from these features, the self-similarity matrix of a given recording would be the comparison of each frame to each other frame. And so if you have a loop, by the way, this was using the earsketch database of 4,000 loops. And then for one of the experiments, we mixed that with some environmental sound from another database. So and this is kind of the specific novelty of this. So previous work has been done mostly on existing music, which is kind of rhythmical all the time. Most of my research focuses on common, like polyphonic music. Whereas here we have this idea of there's a background, and then we need to know when does it start. So we compute the self-similarity matrix, and from here we sum the diagonals and compute the bit spectrum. And here we see some peaks that represent the most frequently repeated periods. And then as a way to find where does the loop start, we select the diagonal corresponding to the highest peak. And then this is the plot on the bottom. Here the difference between, in the left side you have what you would get with a loop that is already being cut and it's already music loop. And in the right side, there's this idea of embedding, mixing the music loop inside the noisy background. So what you find is that the peaks of the bit spectrum are still there, and it's easy to estimate the loop period. But then it's a bit different how to find where it starts. And here what we found is that there is this kind of plateau region. So there is a certain self-similarity in the noisy background. But then there's also this dip, which I think it's more related to the fact that this is a synthetic example. So it's a mixture of some content with some background that is unrelated. So when it starts, you see kind of the self-similarity goes down. But then there is kind of this, there's always this plateau region. And this is the method that we use to detect that where the loop starts, in the plateau in the diagonal. And so the first experiment we did was about detecting the loop period. And here we explored a bit the trade-off that is given by the feature dimensionality. So we took a couple of libraries that were available for feature extraction on web audio as of sort of during the last year. I think there are more libraries presented this year. So here we compared two that were available, and we compared, we measured accuracy. Here in the database, most of the loops are composed of 2 bars. And so basically we defined that loop period within 20 milliseconds of either 1 bar or half of the duration or a quarter of that would be appropriate, it would be okay. And so we computed accuracy as the fraction of loops that were correctly identified, the loop period that was correctly identified. And then we looked at what's the accuracy as a function of the number of descriptors. And also what's the time it takes, because the main point of this is that the most expensive part of this is calculating the self-similarity matrix. And this heavily depends on the size of the feature vector. And what we saw is that there is certainly it makes quite a difference to choose between different sizes and different implementations. And in general, JS extract tend to work better. And as you can see, the rough number of the time it takes to estimate this. So these were loops that are about 7-8 seconds. And it can take about less than 1 second to complete this. So it's possible to do it in real time. We didn't do that yet, but in theory it should be possible. The second experiment, we measured how to detect the start of the loop. And we measured the error in terms of we know because we mixed the loop with background noise, and we know where. So we measured what the algorithm gives us and the ground truth that we know. And we saw that the method we were proposing, we compared it to just thresholding the diagonal that I just showed. So just a threshold is something that has been used in traditional MIR. And certainly the idea of finding this plateau region works better. But there are also, like most of the examples, the error is very small, but in some cases the error is quite large, actually. And so we took a look at what are the errors, and we didn't do any further experiment. But informally, we saw that the errors are usually correspond to outdoor background noise. So the database that we use for the background noise has environmental recordings, some indoor, some outdoor. And preliminary conclusion would be that for the indoor background, it kind of works well enough. And for the outdoor, it may be challenging depending on what you have. So for example, if you have noisy sounds of drums and you have street works, then it might be really difficult to find the loop start. So we implemented this as a JavaScript library. Here, kind of conflict is the fact that, so there is, of course, a short time for transform available in web audio, implemented natively, but it's not guaranteed. So the timing of the hop of the short time for transform is not guaranteed. It's more like thought for visualization and stuff like that. So for this reason, we used our own implementation of the short time for transform and combining this with adapting JS extract to work with this. And then I would like to mention this library called SCJS for basic linear algebra. It's a quite nice collection of modules for the kind of thing you would do with MATLAB. And then we tried, we did a demo example for what we call interactive research. Meaning it's not real time, it's actually you record something and then you stop and then it calculates the loops and it proposes a list of loops. So for the future work, we hope to do a real-time implementation. And of course, this requires this call to navigator get user media, which is now being replaced by the media devices API, and which is not available in all browsers. It works in Chrome typically, and I think now it works in Firefox as well. But so this is still kind of research code. And hopefully, in the near future, this will be available for any web platform. So basically, we have proposed kind of a use case for web audio. The idea that you could much more easily than now, capture loops in kind of casual contexts and potentially using a mobile device. And then we showed that there are some basic signal processing algorithms that can be implemented in JavaScript and that kind of work well for interactive. So at least we've seen an interactive application, and it works well for low noise indoor environments. And then we hope in the future implement this in EarSketch and then do some more user study, also seeing how different methods could be used for selecting the best candidates of the loop that you recorded, and then, of course, implement the real-time version. So that concludes the talk. Thank you so much. And any questions?
Any questions?
For the background noise, was that signals played in an environment and then recording the signal played in the environment, or is that sound just mixed with background noise?
Yeah, it was just a mix, so it could be called a synthetic mix.
I have a question. So I saw that you said you had a demo up there. Is that something that, can we go out in the lobby and try it, or?
So the code is there in GitHub, but I haven't set up the demo. So I can set it up and show it.
And did someone else have a question? Yes, great.
Okay.
You mentioned a time stretcher at the beginning of the talk. Is that something that runs in web audio, or is it on server side offline? Or
yeah, that is kind of an example of the EarSketch context, which is not directly related to this work. It works in a server side.
So my other question was, you mentioned at the end that you want to integrate this with EarSketch, which is the sort of how to program teaching platform that they're using coming out of Georgia Tech. I guess my impression was that they weren't using JavaScript for that. Am I mistaken in that? Like, does EarSketch use Java? Or JavaScript, I mean?
Sure. So this is a web application. So there's a server component that is done in Java, and then there's a very rich client sort of application showing JavaScript. And then the programming itself, you can choose either JavaScript or Python for the kids that are learning how to program.
And so you'll be making something that will be Python programmable and somehow...
No, this is it's more like the part where you extend the database of loops available by capturing new loops. Right?
Okay. All right. Well, then we're doing wonderfully on the time. Can we give another round of applause for the speaker?
Do you have sounds that I can plug in?
Yeah, I haven't tested them. Oh, this way.
Is there a headphone jack over here? Yeah. Can this, yeah. I didn't have a time to really do a good sound check, so I'm doing that right now. Yep, okay, cool.
All right. Well, it looks like we've got good representation here today from Georgia Tech. And so the next speaker is also from Georgia Tech, Zachary Kondak with the Web Sonification Sandbox.
Hi, everyone. So yes, as just stated, I worked on something called the Web Sonification Sandbox, and it's an easy-to-use web application for sonifying data and equations. And this is kind of a joint project between the Georgia Institute of Technology's Center for Music Technology, which I'm a member of, and the Sonification Lab, which is a kind of a multidisciplinary lab that's between the College of Computing and the Psychology Department. Right, so I'm going to kind of start off with an introduction of the background and the kind of the foundational ideas, and then I'm going to go into a little bit of technical stuff. I don't have too much, and then a demo and talking a lot about future work and discussion stuff. Right. So just to introduce like why, what's going on here. So the web sandbox is used to create something called multimodal graphs. And a multimodal graph is just how, in high school or middle school you would have an x and y graph, and you'd graph y equals x squared. It's a completely visual graph. So the idea of a multimodal graph is you take something like that and convey it across multiple modalities. And the two that we're using is sight and sound. So when you use the sandbox, it'll show you the graph, but also you can then play it and interact with it via sound. And so there are two common realms in which multimodal graphs, especially of this nature, are kind of useful, and that's to increase accessibility as well as to increase engagement, which are kind of related. So the main use case I'm imagining with this type of software is if you were, say, a high school teacher or something of that nature, and you wanted to kind of involve the whole class in experimenting and learning about different equations or different types of data, and you were to traditionally you just show a graph and be like, this is what y equals x squared looks like. But if you happen to have some visually impaired students in the lab, or some people who just prefer sound over visual information, then it would increase engagement as well as provide accessibility to students who just couldn't see that graph. And the main benefit of the web sandbox that I'm working on specifically above other tools that you could use to do the same thing is that it's easy. And I will get more into exactly what that means later, as well as you'll see during the demo. So there are some existing tools that can do this. Especially more geared specifically towards sonification is the data to music API, which was presented at last year's Web Audio Conference by some researchers at Georgia Tech. And so this is a very highly specialized kind of fully featured API for live coding in the web environment for creating music from data, right? And so, like I said, it's very full featured, but you kind of have to know how to program in order to use a live coding environment. And the most other common way of actually creating auditory graphs like this is just by using some sort of fully featured musical programming language. So this might be Max or SuperCollider or Chuck, etc. And this work also comes from a long line of the Sonification Lab at Georgia Tech, and they have previously implemented a long time ago a software to do a similar goal as the web sandbox, but this is a desktop application and has significantly more features, and is thus, for both of those reasons, has a much steeper learning curve. So getting back to why the sandbox is easy. So as stated, you shouldn't have to know how to necessarily you shouldn't have to know any special knowledge about sound design, programming, or music terminology notation. So this is another thing that differentiates the sandbox, is that it's completely unmarried from any sort of musical notation. So if it's so easy, how can you actually put in information? So there are two main ways of doing this. You have numerical CSV data. So if you're able to use a spreadsheet, for instance, just export your numbers, and then you can re-import them into the sandbox. You could also manually input tabular data of this kind into the sandbox. That functionality is built in, as well as inputting equations just the same way you might into like a Texas Instruments calculator. So, right. So getting a little bit into the technical side, there are two main ways of creating sounds in the sandbox. There's the synth, which is a very basic synthesizer. You'll hear it. You heard a little bit just as I was testing my sound. It's very simple, but definitely something that we want to expand a lot on in the future. And then the second way is through sound fonts. And this is more kind of how the original sandbox worked, is everything is kind of a discrete data point, and so plays on an instrument. So you select from, you can choose piano, harp, various semi-cheesy MIDI sounds. And so the database, this is not very interesting, but just to say that this is not it's not a static web page. We have users, and it actually saves user information. Right, so now we're going to get into the fun part, which is the demo. I recorded this video, so I'm just going to try to talk over it in sync. Hopefully that works. So, oh, that's not working. 1 second. There we go. So the first thing we're going to do is import some data. So you press New, and then the Edit button. And then we're gonna import some data that I got from the Weather Channel, which is just average temperatures between some years, I forget which ones. So you delete the default data, and then you choose your file. So this is all exactly the process you'd go through. I wanted to show that it's very few steps. So you import the CSV data, and then you press the parse button, and all the data should then show up. And and then you press the save button. Right, and then you can actually sonify it. Once you press save, you get brought back to this menu, and you actually just press sonify. Right, so the data shows up, and you can press play, and that'll play stuff. And so the drum sound you're hearing is called the context cue, which we're sonifying every increment in the X plane, in the X dimension. And you can also go through with your arrow keys and explore the data as you wish. And then, what's the next thing I do? Yeah, merging data. So a big useful part of sonification is actually being able to compare data. So I imported another group of data that's the same year ranges, but minimum temperatures rather than average. And so we're going to just press the merge data button, and it'll bring you in to show you the tabular data again, but you'll see that there's 2 series, and so you can click and see the different data series that you have imported. And then once you press save, it'll create a new entry in your project section that you can actually sonify then. And so now you can see the upper one being the average temperatures, the lower one being the minimum temperatures. So now we're going to have an example of synth to sonify this same data. So you can choose the synth for each individual line. So each line could have a separate sound source. And here I'm just, you press play and you'll now hear the synth. Oh, and I'm going to turn off the context so that drum will go away. So here's just a bunch of saw waves. You can then actually, while it's playing, modify the synth. It's pretty subtle, but changing the waveforms and stuff. And so here we're going to hear another example. I cut right there and changed a few other parameters. And the next cool thing is doing glide. So I'm going to turn off that drum, and then we're going to turn the glide all the way up. And what that'll do is interpolate between each point, so that to create a continuous feel to the data. And you can also go through with the cursor keys, and it'll play for as long as you want. So you can explore the data at your own rate. Cool. Right, and then the next big feature is plotting equations, which, so that's you just press the plot button, obviously. And then I'm going to graph the equation sine x times x squared. And so you'll see a sine wave being multiplied and grow exponentially. And I'm going to graph that from the range 0 to 30. And then all you press is save, and then you sonify it just as if it were any other data that you had imported or input manually. So I'm going to just, I press the right arrow key to play through it very quickly. Cool. Yep, I think that's it for the video. And let me get back to Oh, this is complicated. Anyway, I'm just going to present it this way. Yeah, cool. Anyway, so a big important bit is the future work, right? Because we need to actually evaluate this, because it is certainly visually a lot less difficult to understand than the existing tool, which is the sonification sandbox from the sonification lab. But we need to kind of set up users to, in an environment and give them some example tasks and see how much easier it is and how much easier they rate it and actually how fast they're able to accomplish goals. And then another big one is accessibility, because as stated before, we really want not only the teachers to be able to convey information to the visually impaired, but actually have the visually impaired individuals actually be able to use this software without any assistance. So the future working from the technical side is expanding the data mapping, because if you notice, the data series are really only mapped to frequency information, which is, it's okay, but there's definitely a lot more that we need to be able to map to, especially for sonifying data sources that may be two-dimensional. Maybe we can map one parameter one dimension of the two-dimensional data to different parameters of one single sound source. And then as that kind of happens, we would then need to incorporate a lot more music perception kind of stuff, like equal loudness curves, to make sure that the data doesn't become completely non-understandable or convey incorrect information to the user. And then the synthesizer needs a lot more features in terms of things you can modify, the configuration of it, different tunings and things like this. And then with that, to maintain the easiness of the software, then incorporating the preset functionality. And then plotting. Right now, the sampling rate is hard set from whatever range you pick, which is definitely something that needs to be expanded upon. Right, so the conclusion here is that auditory multimodal graphs can be very useful to a wide range of people. Right now, all the tools require some sort of expertise to use, and so we feel that this kind of tool, especially on the web where you don't have to install anything, is much needed. And thank you.
Questions?
Hi, Bob Smith from Chiranga and Bryan. I'm just wondering, as it is on the web, is there any kind of live API kind of?
Yeah, for sure.
So can you tie it into something that's kind of live data stream?
That's definitely something we want to do in the future. Right now, it is just a web application. There's no API to tie into right now.
Well, while I'm walking that over, I'm going to take this opportunity to ask a question myself. I saw that you were mapping only onto frequency right now. Mm-hmm. Do you have, how much control do you have over the mapping? How can you make it nonlinear? How do you control that function?
Right. So right now it's just the standard logarithmic, and it's done that way because we wanted to hide every difficult aspect from the user. So it's just the standard logarithmic scale, and it's hard mapped between a set frequency range. So whatever your data is that you put in, the maximum and minimum of that data will be mapped to whatever the maximum and minimum frequencies are right now. So it's not dynamically mappable.
Hi. My question relates to that a bit. I think what I like about it, it makes like data, you can feel data, it's more emotional. But I think you have to listen to Schoenberg and Poules all day to feel this.
Yeah.
So are you thinking about making it more harmonic? Or?
Yeah, I mean, for sure, incorporating kind of tools to make things more pretty. I think that also comes a lot with making the synth more modifiable, because a lot of you can make it sound maybe more atmospheric and more subtle than square waves shooting into your ear.
Okay, I'm going to use this opportunity again as I walk over. So one of the thoughts I had when listening was it would be nice if, for example, can you assign different synth patches to the different streams of data?
Yes, we can already do that. So
Okay.
for instance, you can use a piano sound on one and the synth on another data stream.
So my question is generally around sonification.
Mhm.
So I was wondering if from the collaboration you do with people interested in data exploring, is there anything that sonification reveals from data usually that visualization doesn't? So is there like, what's the biggest benefit of sonification?
Yeah, it's very context dependent. Now, in my specific lab, working under Dr. Bruce Walker, his main focus is in accessibility. So a lot of my research is in accessibility. So obviously, in terms of that domain, if someone is visually impaired and they want to learn the concept of a graph or equation, getting that feel of continuousness is really difficult, but sound can obviously provide that fairly easily. So that's the main kind of benefit to using sonification in this context. But in terms of people without vision impairments, there is a lot of work discussing things that can do better, but I'm hard pressed to find specific examples right now.
Okay, is that all the questions? Okay, then let's please give him a big round of applause.
Thanks. I'll just go around.
Oh, well.
Well, as you all know, these days in science fiction, future dystopia sells a lot of tickets in the box office. And I believe this next talk is going to be giving us a view of diamonds in dystopia. So
That's not it.
that's not it?
Hell no, it's flipping around. Does anybody remember where they've moved it since the last spot? Last time I remember.
Where they've moved what?
It's showing the presenter's thing on the wrong.
Switch on mirror.
Which one?
Mirror thing. And the same.
Yeah, we've gone
Well,
for
we're seeing a bit of a dystopic
Yeah, that's right.
present right now.
That's wrong.
In a world where no one can use projectors.
I know.
One solution would be for us to all gather around your laptop and
That's
then you
always
can
the
look
best
at
way to
this.
do it, right?
Then if I don't get it, then you're going to be mad at me.
It's not for mirroring, though. I want it to be switched between the two.
Do you want to unsettle? Yeah. Go on.
Yeah.
So that's, no, not on the computer settings, so if you don't, yeah.
I'm trying not to mirror. One spot. 7 minutes. That's good.
If you go to the general settings, not the Keynote settings, have you tried it?
I got it.
Okay.
Thank you. There. Hey, here we go.
All right, so Jesse Allison, please tell us about active server roles for extended distributed performance complexity and diamonds in dystopia.
That's right.
Still in your microphone.
Oh, thank you.
Forgot to give it back.
All right. That would be the extra complexity here. So my name's Jesse Allison, and this is the background of a work that I produced with Derek Ostrenko and Vincent Salucci that'll be performed tonight. It's the first piece on the concert tonight. So you get to see a lot more about the actual work at that point. But I wanted to talk about the approach to the back end today. So this all comes out of work in distributed performance systems. And I wanted to mention just a couple that are really excellent pieces. So the IRCAM SoundWorks, which was talked about a little bit, or an extension of that was talked about this morning, and the Rhizome project by Sebastian Picomel have been just great frameworks for distributing and getting user interface and performance stuff distributed out to mobile phones and web browsers. And what they tend to do, the projects tend to facilitate connections between people, sharing of data, doing a little bit of rendering actually on the devices, on the client devices themselves. But the server, the way that that functions is basically as a way to connect people. It really has a lot of load. And basically they kind of shy away from taxing either the client or the server. And there's good reasons for that, because if you do tax the server or the client, it tends to fail. Right? You can't get up in front of a live performance and have a lot of processing and things happen, and a lot of network communications happen, and have it crash, because then your performance just dies. However, there's a lot of opportunity to actually taxing the server or taxing the individual clients as well, and that's what I wanted to look at here. The work that I've been doing over the last, I don't know, 8 years, 10 years now, has been in doing this distributed types of things with servers to be able to distribute communications. And it was a project called Nexus that I started in 2008, 2010, which developed into a UI project and some other things as well. But I was going back through and kind of cataloging what I'd been done and where this was coming from, and I found a couple slides which I thought were kind of interesting from a prior presentation. So this was how I viewed things about 8 years ago, that the advantages to doing web distribution ended up being things like being able to share it with anybody, right? Being able to have it be scalable. A performance is scalable. You aren't just making a single instrument that someone could perform. It could be n number of performers, and then they could just be aggregated into a live performance. The idea that you could have lots of people sharing resources and sharing computation, it's a big high performance computing kind of issue, right? And then you would needed tools which have been developed or are being developed on handling all of that communication. And one of the reasons I liked that was that the web browser was everywhere, right? That you could even find it on your fridge. So coming from, yeah, it's a new music instrument right there. But coming from that background, I was working on projects like this. It's an installation called Humming Mississippi, which took data from the Mississippi River, sonified it, played it, actually these panels of wood played the audio that was being generated, and we made a web interface that communicated between anybody who was on the web, but then also started playing music on the physical installation. So no matter where you were in the world, you could participate, just in a different fashion than if you were standing in front of it. And these are just two of the visualizations, the things on the right here, that we generated for that, or the interfaces for it. While I was presenting this for the first time at NIME, I think that was in 2013, I think that's right, my university at LSU was decommissioning, well, installing some new HPCs and decommissioning a couple of old ones. And an email went out while we were at this conference saying, does anybody have any need for nodes, a few nodes of these HPCs? And so Derek Ostrenko, my collaborator in digital art, and myself raised our hand and ended up getting about 448 cores of decommissioned supercomputers, which was great, because we had tried to use some of the HPC resources that were available at the university and that sort of thing, but they are not designed for doing audio or doing art, period. They've solved so many problems, but not the ones that we deal with. And so we were able to get one that was completely offline, nobody else had access to, so we could work with it, break it many times over, and find out what we could do with it in an artistic context, right? Typically with sciences, the HPCs are all set up with these, where you basically submit your work, and then at some point in the future, it's scheduled to happen, happens, dumps data off, and then you go back and get your data. And it just doesn't work for very many artistic purposes in that way. So from that, we started working on other types of distributed performance things, where we were using, was Ruby on Rails and then Node, once that became more popular, to make artworks. This was my first collaboration with Vincent Salucci, who's a poet there, where we used a poem of his called Causeway and made it an interactive version. We made a performance version that was done live, where the visualization was created on the server and then played into a theater, streamed into a theater. And then the audio was actually generated for a 92 channel array that was performed. And then this is an installation version outside of the performance hall so that people could get used to interacting with it, with their cell phones before they went in for the performance. I love this picture. I love this picture because no one is actually looking at the installation. Like, I think that's one of the kind of interesting problems with using our cell phones, period, but in art as well, right? If you'll notice, that little girl is behind it. But she's still participating in it in a meaningful way. It's really an intriguing kind of a, I don't know, paradigm shift, something that people should exploit, try to use in their art. So out of these things came this piece, Diamonds in Dystopia, and I'm just going to show you a little blurb about it to give you an idea of what it is. There we go, a little video. It's fairly short. You'll get to do this tonight, so. It's a live reading from the poet. So I think that kind of gives you a little bit of an overview. Essentially, the thing is the system that we've developed is doing a lot of things at once. And as a audience member / performer, you're very taxed to where your attention should be in the whole thing, whether you should be reading or listening or interacting with your device. But essentially, what's going on behind the scene here is that we've got a web portal that happens to the interactive poem. And as you touch any of the words on the poem, it goes off onto the server and generates Markov chains of phrases, so new generated poetry that's sent back to you, and also sent to the person who's reading the poem. And on stage, the poem that the poet is reading, he's working on or reading the poem and then also integrating some of the things, choosing which verses that you've generated as an audience member to integrate into it and add into this poem that's going on. There's a visualization, there's sonification, there's stuff happening on your device as well. So all of that's kind of going on. But that brings up the question of what does this actually look like? And it looks like two things, actually. In practice, is a ton of tech behind the scenes, right? So this was the first performance that we had. If you'll notice, the poet is actually sitting there with an iPad and a phone to deal with what he needs to deal with on stage while he's reading. We just have a chain of, I think we had 3 computers at this first one, and then iPads and some other stuff that was happening. And I love this because it's a good indication of all the complexity that's happening, but really there's a behind the scenes for behind the scenes, and that's the server side of things, right? All the stuff that's happening up there. Like the distributed performance with communication to all these different clients and users. But there's, what my presentation is on is actually what we're doing internally inside of the server to be able to make some of these other things happen and add to the types of art that we can actually create. Yeah, so on that note, there's two things that I wanted to focus on. And one was the generation of the phrases that we created. So to be able to do these Markov models and finding and generating new phrases, we took 2,050 TED Talk transcripts. And then we used the Rito library to do some natural language processing stuff on them. And to do that, to prepare it to be able to pull it and have it generate new phrases based on words, it actually creates a model that takes up about a little over a gig of RAM, right, to be able to do it. And then it takes a variable amount of time to actually query it and then have it respond with legitimate phrases or illegitimate phrases, depending on which things it's pulling from. Which meant that we couldn't throw that onto the client, right? You can't just pull up your cell phone, download a gig of data, and then have it process it. We needed to do it on the server, and we needed to be able to support this for many users, which caused some serious problems. So basically to do this, we ended up creating or making a bunch of worker nodes, because every time you queried it and it was doing the processing, it would block how much other communications that needed to be happening for the performance as well. And I'll show you that framework in just a little bit. But that's the problem, is that we had a task that needed to be done for lots of people that used a lot of data and used a lot of processing. There go, server, HPC. All right, so the other problem was this one, which everybody knows. As soon as you do a performance, that's what the tax on the system looks like for every performance. Nothing, everything, nothing again, right? So to be able to work with that is incredibly difficult. And this is something that has caused some serious problems. Some of this is able to be negotiated either on the client or pushed off to the client, and other times you can do it internally. But this was one of the issues that we ended up running into with diamonds in particular, was how much data needed to be transmitted, how much data needed to be processed before it went on. Cool. And then the last one is just a little bit about the shared performance side of things. The visualization was done on a separate machine. I have an audio that's created as an aggregate of all of your interactions for the audience, and so that's on its own audio machine. Technically, it could be the server, it could be a local device that's optimized for that, but essentially it's offloading some shared experience stuff onto another machine so that it can handle the processing, and you guys don't have to. You can just handle your interactions locally. The best parallel that I've seen in this is through like massively multiplayer online games and like Second Life, that kind of VR experiences. But a lot of those tend to do very similar things where they're just facilitating data communication. So if somebody moves over here, it's just sending the movements to another location. And it doesn't deal with having to do large-scale processing types of things. So things that could be used besides just audio generation, video generation that would be done on a server would be things like doing MIR, music information retrieval things for large groups of people, or doing machine learning or deep learning types of aspects. It doesn't have to be local. And so that is what we did here. In our instance, to be able to solve some of these problems, we ended up doing some Redis server for very quick. It's a data storage that's in RAM, so it's very fast. I think the last application we did was 50-some gigs of RAM, so it could hold all the Markov models and generate stuff really quickly. And then we did a node cluster with 16 workers to be able to handle the various people that are querying from the audience and responding in almost real time. There we go. So I wanted to mention one last thing, and that there's other things that need to be addressed heading into the future. Well, a huge one was testing. Like, how in the world do you test this sort of thing when you get, for that performance spike with many, many different clients, many concurrent messages. The data logging to be able to find out where failures and things occur. There are a lot of things that are built for that, but they tend to add a little bit of lag time or that sort of thing, and a lot of that we don't want to have when we actually do the performance. massive storage, massive computations. And a lot of these things have been solved for the HPC community, but not necessarily in a live and performance environment. And so these are still issues. They're going to be issues for a while, but trying to adapt things to be able to run in real time and to be able to facilitate what we're doing artistically is an interesting problem to go through. All right, I've run out of time, so that's my last slide. Thank you so much, and if you have any questions.
I see one up there.
Do you have any natural language processing code directed towards controlling syntacticality, for example, tree structures?
No, not for this, no. That'd be a great place to work on, yeah.
So you mentioned all this high-performance computing stuff.
Yeah.
And I saw a giant server rack, and I see that you're going to be doing a performance, I guess, of this tonight?
Yeah.
So how is that connected
so
back to Louisiana over the web?
We've done two different versions of it. One that we spin up on Google Cloud Compute Engine, and then run it from there. And then we've done performances where we do it from the server back in Louisiana. And for this one, just to keep lagging stuff down, we've done it on Google Cloud on Western Europe. And there you go. But yeah, we've done both.
So you did two performances, and how many people were attending those performances, and how many people?
It's live. We had a little over 100 unique devices connected to it in that 7 minutes.
And how was, like, what was your capacity? Would you be able to scale further, or?
So yes and no. There's a few issues that are really problematic, and the one being that when you first load up you have to get all of the data. Anyway, so all the audio files, there's a bit of JavaScript framework. When I created this thing, I couldn't do, I needed to do some speech synthesis because I didn't know what kind of phrases were going to be generated, and I wanted your devices to read it. And the built-in web browser speech synthesis, you can't run into web audio nodes. So there's a little framework that gets loaded over there, which is a couple of megabytes. So at any rate, so you can see there's a huge spike right when you do it. When we got around that for one of the performances by doing the installation beforehand, which meant that people had loaded up the page. And so when they came to the same thing, it just, but unless you're doing some sort of trick like that, that's a huge limiter.
Okay, let's have one more round of applause.
Thank you.
As I was looking at the program for tonight, so you all know that there's a performance, as he's alluded to, around Bethnal Green. It's all in the program, but one of the things you might not have noticed is that 4 of the 6 speakers today in this session will be having their music performed tonight at 8 o'clock. So a lot of the technology you're seeing described now, well, I think it'll give you a bit more appreciation of everything that goes into the concert that you'll hopefully attend this evening. And one of these, besides the person we just heard, Ariana Stolfi,
yes.
Stolfi, sorry, is another one of the people that is not only talking right now, but will also be performing. And is the thing you're going to be doing tonight related to your talk?
Yes.
Wonderful.
I'm going to see that. What's the engineer?
This is provocative. We're already getting a preview of the music
Yeah,
performance.
we're going to. Oh my God.
Could you say something about the venue tonight, where that is? Is it
Do you have an HDMI entry? Because I don't see.
Okay. I need to deal with that. Okay. So, are you from around here?
This one?
Neither am I. But what I can tell you is if you go to the program webpage, you'll see that for 8 p.m. it says Concert 1, Oxford House Theatre. And if you click on Oxford House Theatre, it gives you directions to there. It looks like it's in Bethnal Green, and there's actually an address and a linkable click-through map. And if I click through on the map, let me see what I get to. It's a 20-minute walk. Do they? Because yeah, the Stepney Green and Bethnal Green are not attached on the tube. Is that correct? It's not the same line, so you'd have to change lines if you did that. Yeah, but if you go to the program, you go to the 8 p.m. show. You click on the Oxford House. It gives you map directions. Oh, maybe you should.
I'll display the map for people later. Just, I'm sure you can all find it really, but yeah, and we can maybe group together to walk, I guess, so we don't get lost.
Oh,
okay, are you ready to go?
Okay, I'm going to talk about this project, Open Band. I'm Ariane. I'm from the University of São Paulo. I'm developing this project with my partner Fabio Gorodsky. I'm researching PhD on music at that, and he's on computer science. And we have the help of Mathieu Bartet, who's my advisor here at Queen Mary, Fernando Iazeta, who is my advisor at New Song Research Group, and Antonio Dozani. The New Song Research Group is a research group basically on sonology, that we research like process of creation and perception and every kind of art related to music and sound. We develop also interactive sound systems and artistic production, interdisciplinary interfaces, and music acoustics and whatever. So for me, that I'm architect, and I came from a background in web design research on the master. The song was a very good place to arrive on music, because they are very receptive of every kind of experiences and non-traditional music, and that's why I'm interested in developing in my PhD. So I am very interested in particularly the view of Open Echo about open work. Oh, Open Echo, I say Open Echo. Umberto Eco about open work. It was like this kind of works that can be shaped by the audience or can be interpreted. There's like several kinds of different ways to work with that, but we choose like this project very specific standpoint. So Open Band was called Banda Aberta in Portuguese. It's like an interactive music performance with a web chat interface. So when the New Song Research Group was invited, I think now it's 1 year ago maybe, to do some participatory, some experiences in a festival that was in an open square in São Paulo, we started to discuss how to make some kind of interactive stuff. I was already doing some very low quality experiments with web audio. I did like a keyboard that you could type and send samples. It was very simple. And then Fabio showed up with this proposing of doing like an interactive synthesizer that everybody in the audience could join and play together. So we joined our projects and said, well, let's do a chat. So everybody types, and for each letter there will be a sound. So that was the first project. So like in 1 week that was already done, the first version, and we started to work in more sample packs and stuff to do like this idea. So our idea at first was to use all the potentials of the audience speakers. So every cell phone plays the same song, the same sound, or every computer, whatever. We have like lots of videos about that because we've done already in a lot of places. In the end, we always connect one of the devices to a PA because the sound gets very enhanced. And then I'll talk about the setup. So the setup for the performance is very simple. We have like one computer that is connected to a projector and to the sound system, but it could work without it also because we have the sound coming from every device. This is the same sound played. And we have like two pieces of software, different pieces. One is the server, who is Ruby. It's very simple. It's just get the messages and then sends the messages back. So it doesn't get any user data or any audio data also. It's just like messages, text messages, simple text messages. And also we have the other piece that is Banda, who is like the main piece of HTML and JavaScript. JavaScript and HTML and CSS, it's very simple. The interface is also very simple, so we choose like, because I was like in a brutalist architecture school, so I got like this very strong influence, and we choose to keep the interface as simple as possible, so it just has text input, so you can type in and press enter, and the messages come. Now for this one that I'm going to present today, we have like spectrogram also. So we're going to see some more enhancements, the performance. We did a lot of performances with that. So we started in the Bigorna Festival, it was like that. Just like he said, nobody's looking to the screen, everybody to the cell phones. And we don't have like a very important role in that. Actually, I act more like a conductor. So everybody's typing and I can change some things about the sound. In the first version, we have like 4 packs of samples. But everything can be controlled through the interface. So I have like special commands, like text input. So if I type something that I won't tell you, I can change the sounds, or can change like the dynamics and can make everything go out also. We have this online version working every time. So if you enter that, you can make some noise right here. And sometimes I just change the home page because today I'm going to present a version, tomorrow is another, so I keep changing the index. But this is working all the time. But we did like in Bigorna Festival, we did an Audio Insurgência, who's like an experimental musical festival. We did it on the radio also, that was very nice because people really listening to the radio. We did it in a symposium, academic symposium. We did it in a concert of computer music on IMI. It was like pretty cool also because people from the audience was like hackers and they start to send CSS to the chat and things starts to walk on the screen and square geometrical shapes showed up also. It was pretty cool. This new version that I'm going to present today, we present on Musica 12. It was like a festival of the New Song Research Group. And I present also in the SHA Festival and the Techno-Shamanism meeting last week ago. So the first version I made with samples. I won't talk too much about it because I'm going to talk about it in the Audio Mostly conference, about the semiotic translations and how do I change the samples and that. It was like a very, very large amount of samples because it was like 4 samples packs, and for each for one character. So it took like a lot of time to download. So we have always to make a local network to don't spoil the 3G data of people. And we have like fixed collection of samples that was determined by me, the composer. And we have some necessity to control more the audio flow and audio processing and stuff. So we started to think about it in doing a version with web synthesis. So that's the version I'm going to present today at the concert. You're going to see a bit now. But when I started to think about it, I remember of a work that I made like 7 years ago. It was like his play just because it's very quick. It was like done by spectral cutscene. So I just made like letters by cutting the spectrum, and it was like a saw sound in the back. And I had much interest in typography because I was like studying graphic design, and so I had made some modular fonts like that. It was like letters made of blocks of things, like that one also. That used to installations. We used to make like banners for meetings, student meetings, and all sorts of stuff with that. And then I studied a bit of typography and design. And I remember this one from Douglas Hofstadter, who's like in the Metamagical Themes, the book. And he says about the metafont. There's an article about the metafont, which was developed by Donald Knuth. I think metafont is used on LaTeX to make the fonts. And it's a very parametric font. So we have like lots of things that you can change to make the fonts different. So I started to think about making something on audio typography by using some it's not like that with thousands of parameters. In the future, it could be, if I have time or if I have will to do that. But I sketched this. It was like a very schematic letter that we can make by adding some sound functions to draw the letters on the spectrum. So in the end, this is the font, the font family. And we have like these functions, these horizontal functions, who are senoids. They're like senoids, static senoids, and glissandi also for the diagonals. And these ones are blocks of noises. So we made all this. It's very easy. Like that, we have like groups of letters. So each letter plays some kinds of functions to make one letter together. The web audio synthesis is very simple. We use like pure web audio for the sign functions. And noise blocks, we use the framework called Noisy that we developed especially for this project, but you can use it on GitHub. Everything is on GitHub on this project. So we can draw blocks from one frequency to other, and I can change these frequencies in real time. And I will just show a bit very quickly. It's a bit messy. Okay. Yeah, there's someone already talking, but it's like this. This is the admin interface. The sound is very low. But they draw these functions there have like light condensed, medium condensed, bold to change like the time intervals. And I can change also the frequencies and the base frequencies or whatever. So in the future, now I'm joining the Audio Commons project, and so I would like to join this project with the Web Audio Commons API, maybe to do like people choose the samples, to use the frameworks, a lot of things that you can do, like make multiple voices and a lot of stuff. So that's it. Thank you.
Okay, just to make sure I understand sort of what's happening with this. So somebody types something in. This gets turned into a font that you have developed. And then this font is translated into sine waves that are going up or down and noise bursts so that whatever they type becomes a particular sound. Okay.
Yeah, it's basically that. The first version is not simple. So like you type an A, you sound like an A in the application. So if several people type together, they come like it comes like superimposed, so it's quite chaotic sometimes. But you have like for each letter, we have groups of functions that are played together. basically that. Everything is on the browser.
So you have literally created a sound font.
Yes, audio type.
That's nice.
Other question?
Well, I'm walking all the way up there. So I'm a little confused about what happens when multiple people type in something at the same time. How do you keep it from becoming just one big...
It becomes one big... So like if I keep pressing it, it's going to... And it's going to become like really noisy in the end. But I like it, I don't care.
Hi. When you introduced your audio font, did it change the way people were interacting with it? Did they know that they were using your audio font, or did they just think of it as noise?
Depends. Some people know, some people don't. Like in the I just presented this work once because the other one was with samples, so the people could actually know what they are typing. But in this new version, it's more difficult to recognize the letter with the sound. So maybe there's like simple things like this. If you got like slash like that, it's more easily because it's just like bars of sound. Take a bigger one here. It's more easy to recognize, but depends if you know what you're doing or not, because just some people go in the hall and say they will not know exactly what to do. But now with the spectrogram, I think helps a bit. But it becomes like very confusing. Yeah.
I guess my next question is, my particular feeling about Brazilian Portuguese is that it is a very pretty language. And so it occurs to me you can type things in your sound font in different languages. Is there a language that you find produces prettier noise bursts?
Actually, I don't think so, because it's just very abstract. So, but in the other version, what are different are the cultural differences and the audiences. So, like in Europe, I think when I present open band, people try more to do the sound, and sometimes when you go like to young people in Brazil, they're just typing bullshit, but it was not really different in the sounds like that. No, but I think here people are more civilized. They like type a sound and listen, and so yeah.
Speaking of typing bullshit, I'm thinking maybe it would be fun for you to type a few Donald Trump tweets to see that.
Yeah, you can type whenever you want. The main thing is this is anonymous, so nobody knows who is typing what. So you can type whenever you want. In the concert, you have the chance to type whatever you want.
Okay, I probably shouldn't make this political. Any more questions?
Nobody will know.
Any things now? When we come to the performance tonight, will we be able to somehow participate?
Yeah, you're going to participate. I hope the router stands because it's like lots of people. I have like but everybody can connect. I hope you have your cell phone charge, and with the laptop is very faster also. So you are all going to participate.
Okay, last chance for questions. Then let's give her her first round of applause. We'll give the next one at the concert.
Thank you.
Oh, this is exciting. Now you two are not performing tonight, right?
No.
Yeah, so I see you're performing now.
We will make some demos tomorrow.
Okay.
I must say that I'm very happy to see women at this conference presenting. Because in the previous year, the previous version of this conference, we had not a lot of women. So there is an improvement this year. It's really great. Quel micro? C'est quel micro? No mic?
Who's got the microphone?
Yeah, sorry.
Actually, and I want to thank all the presenters because unlike many, I'll just say it, when I do this kind of thing at ICASP, the electrical engineers tend to be much more enamored of their own voices and therefore need to have a much sterner hand cutting them off. And here at this conference, everyone's been wonderfully polite on the time so that we'll all be able to go to lunch when we hope to go to lunch. So I just want to thank all of you for being so cooperative and understanding of the time.
Tu as branché la ligne là? Elle n'est pas branchée. Hein? Ah, can you plug it? Ah, ok. Ok. Vas-y. Branche l'adaptateur. T'as pas l'adaptateur? Non. Attends, j'ai pas l'adaptateur. Is it working? Yes. Okay. Yeah, it's going to be enough. Okay. Okay. Perfect.
Okay, are we ready to go?
Yeah. Okay.
Michael Booth.
I start with a few rock and roll, if you don't mind. It makes me in a good mood before the presentation. No sound is going out. Why is the... There's no sound. Should be sound. Yeah, that's it. What? Oh, it stopped. I wanted sound.
You need to be close by.
Close by? Yeah. Where is the sound? It worked, and then
it's just come out of the jack, right?
Yes, it comes from there. Okay. I got it. I clicked on the wrong button. Okay. Let me just adjust a few settings. We can start. Okay, so my name is Michel Buffat. I am from University Côte d'Azur in the south of France. And I'll be more a vintage guy today, because we are going to talk about the simulation of a classic rock amp, the Marshall GCM 800. We had made some modifications to give more versatility, but it's about competing with native applications. You saw when I played that it's real time, you can play guitar in hands, and this summer I was in a small village in the Pyrenees and I made a gig with some friends in a small bar. There were only 63 people in the village, so not a lot of risk and no connection. That's good too. So you can see some pictures of people in my office playing guitar for blind test, and we'll talk about this later. So the software is online and open source. There are two versions. The one you saw with frequency analyzers and probing tools to probe the signal on the different part of the chain, and one that is without frequency analyzers. You must notice that the one with the frequency analyzers breaks a lot of things in Chrome and Firefox, especially the Web Audio Debugger from Firefox and the Web Audio Inspector extension from Chrome, because I'm using ES6 classes that extends Web Audio nodes, and this is not supported yet by the debuggers. So if you want to try this version, disable the Web Audio Inspector. Okay, so why did I do that? First, because I'm a guitarist and I wanted to write an amp sim since I tried Amplitude in the early 2000 years. Then, as soon as Chris Wilson put online his input effects demo that used the web audio for processing microphone input, I started plugging my guitar on the computer. And when I saw that on a Mac, there was the bearable latency, I started researching about how a guitar amplifier works. So on the right, you see Guitar Rig. That is one of the state-of-the-art native applications used by many musicians in studio. And on the left, you can see different versions of real amps combo versions, 2 a head and a body versions, and so on. So when I started to work on that, I first created my own amp without really knowing how a guitar amp worked. But then I met some guys, some authors of native amp simulators that helped me, and they told me, look at the schematics, look at how a real amp works, and try to follow the rules that all the amp designer followed. So I started to recreate the Marshall GCM 800, first because it's simple, second because we can find many existing simulations and many people described its internals. So in an amp, you've got first different modules. The first module is the preamp, and you can control it using the volume knob. Then you've got a tone stack, the treble, bass, middle, and knobs like that for adjusting the tone. Then you've got some extra modules you can find on some amplifiers, like an equalizer, or like a tremolo, a reverb, and things like that. Then you've got the power amp, and this is the back of the GCM 800. It's the most famous version because there are versions that use transistors too and so on. So you've got the power amp on the right, and you can see the preamp tubes on the left. There are different models, and are used to shape the sound, to make the grid distortion sound you could hear. And finally, you've got the speakers. And the speakers play a very, very important role. If I switch just the speakers from my own amp for a Mesa Boogie cabinet, for example, the sound is completely different. So the speakers are very important. Okay, so what did I do? As I told you that I discussed with a famous native amp author. He's called Alain Poulain. His name is Le Pou on the web, and he wrote maybe 12 very well-known and appreciated native amp sims. He sent to me this schematic with handwritten annotations. And he told me, look, there are filters. Look, there are valves. Look, there are the different modules. You can identify the power amp, the tone stack here, and so on. Try to do them as accurately as possible. So with Web Audio, we've got filters. Most of the filters will be recreated using bioquad filters from Web Audio. Of course, we had to look at the schematic to get the frequency, the attenuation, and so on. Then you can create a signal chain with Web Audio just by creating each individual component. So a filter, when I had a tube, I'll come to this later, we used the wave shaper and so on. And then we connected using the connect function from the Web Audio node, we connected the different elements. So that was the big principle. But it's not so simple because some parts of the schematics could not be emulated by putting filters in series or in parallel, for example. The tone stack from the arms that you see an extract of the schematic here cannot be emulated, cannot be recreated 100% accurately. There are famous research papers by David Ye, who is well-known in the field of amp simulations, and he proved that this cannot be done. But he provided C++ code for most classic amps, and his C++ code is used in many native amp simulators. So what I did is I transpiled his code into JavaScript with mscript10, and then put it in a script processor node. Like that, the buttons we have exactly like on my real amp. I've got a Marshall amp at home. But because of the script processor node, if you played with the GUI, you could hear crackle glitches and so on. So it was not a valuable solution. So finally, this part has been emulated by putting filters in series and doing some tests, some blind tests with users, spending a lot of time. The tube are also difficult to emulate because they are non-linear components. On native amps, what people do today, the state of the art, is to do physical modeling, entering the schematic in a software like Spice, generating C++ code, optimizing the code, and so on. With web audio, we cannot do this because I already told of the limitation of the script processor. So we use the web shapers, and I discovered that many existing commercial multi-effects like the Pod XT use wave shapers inside, associated with filters and with oversampling techniques to remove sound artifacts. So what we did is that we wrote a sort of distortion factory, a factory to make different transfer functions for the wave shaper nodes. We spent a lot of time understanding how they worked and why a particular shape gives a particular sound. Asymmetric transfer functions produce odd harmonics that are warm, while symmetric transfer functions produce even harmonics that are maybe more bright, more clear, and more colder. So this is an extract from a very interesting website called Effectrod website. The guy explained really in details how tube works and how they could be approximated using transfer functions. So maybe you heard about the bias on an amp. When you put a tube on the amp, you can tune it. Sometimes you've got some screws, some variable resistors, or in the old time they had to add solder on it to change the transfer function. So you can adjust the way a tube will behave. And in the Marshall, you've got both asymmetric functions and symmetric functions to generate in the preamp both types of harmonics. Okay, so if you look at a simple wave shaper node, okay, this uses the transfer function from the web audio specification, and it's a bit like that. It's not a nice sound. It's a bit harsh. So what we did is that where is it? Okay, so yes, I collected from different libraries, different papers, all sorts of transfer functions I could find. I found the one that has been measured in the preamp of the GCM 800. So all these functions here are in the code and can be switched using a menu just to see the difference. So for adding more versatility. The power amp, the part on the right of the schematic, is a push-pull design on the Marshall, and normally it's used to cancel the even harmonics. The even harmonics are the warm ones, the bluesy ones, the tubey ones. But in fact, we discovered that first it was a bit difficult to implement exactly this schematic, and then that the speaker emulation that is just after this stage plays a more important role. So what we did is that we just simulated that using a smooth, slight symmetric transfer function. So this part is not really recreated accurately. It's for improvements, but the sound is quite good. So the reverb on the speakers have been recreated using impulse files and a convolver node. And beware of your files. I thought first that they introduced latency with big files. It was just my input files that started with some blank parts. So also the amplitude, you must have normalized impulse files, or otherwise the volume will change and so on. And we added finally an EQ on the right, just to be able to shape the sounds better. The GUI is made of web components. Each button, each slider is a web audio control component. It's a famous library written by a Japanese guy called G200 kilograms. I don't know. I haven't seen him, so I don't know. I only talked with him, and we contributed a lot to this library. We added MIDI-learn features. We upgraded it to a Polymer 2 version. So this is what we use. So the MIDI support is in the component themselves. If you use the library, you will get the MIDI-learn for free. And in my office, I I'm using this sort of MIDI pedal controller or this Novation launch control. So, okay, so demonstration again. You can try it without a guitar. If you just play some samples, okay, let me put my glasses. Okay, let's try an example here. Okay, sorry, the volume. This is the dry sound without the amp. So these are direct input guitar samples. Some I made by myself, some I create from the internet. So you can try also. This is okay, and what you see here are the different filters, the different components from the schematic. So you can try, if you know what you're doing, you can, for example, boost the gain between the different tubes in the preamp, or you can change the filter values and so on. Here you've got menus for changing the transfer functions. If you want to try other ones, you can change the parameters from this transfer function and so on. 1 minute, okay. Okay, so it works. Let's quickly have a look at the difficulties. The main difficulty was the latency. So in the paper, you've got a lot of explanations. So you saw it could be played real time. Let me just show you a professional guitar player using it. Oh, sorry, it's not here. Okay, so can you guess what is the latency value here? Okay. How many? 20. Okay. Actually, the real latency we measured from putting a microphone on the guitar and recording the output is 33 milliseconds here. So this is the real latency, end-to-end latency. And this guy could not notice the latency. He said it's perfect. It's not noticeable. So compare with native guitar rig, with native applications with the same audio buffer size, we are competitive. It's 17 milliseconds. So, okay, you can see details on the paper because we measure different sound cards with Firefox, with Chrome, and so on. So, for the future of web audio, we really need improvements on that part in the implementations. We cannot really set the driver, the audio driver sample size today. So we are stuck with 512 samples. Actually, it's 2 times 256 samples because it's double buffered. This will give 11 milliseconds intrinsic in the buffer. Also on Windows, it's unplayable. There is no way to do what I showed with Windows. It's maybe 50, 60, I don't know, several hundred of milliseconds. It's not playable at all. So we need a solution. And also recently, the web audio thread on Google Chrome changes its priority. So I discovered that when I use this with other web audio applications, the threshold where it starts crackling became lower. So we really need a way to compete with native applications. Okay, and about the good sound, how can we make a good sound? Just make a lot of blind tests, user testing. So this is the tubey sound, and I will. Okay, let me just go a bit bit further. This is Jimi Hendrix playing. Okay, and I conclude with the last one. Okay, I've got other videos, but okay. So what we did is that we turned this amp into a web component for using it in a pedal board. We will show that tomorrow evening. So we started working on the web audio plugins that could be interconnected together in a pedal board. You can zoom in, you can turn the knobs and so on. And the amp is just one line of HTML here in this code. So we started thinking about web audio plugins. I know that there will be a presentation this afternoon and other people started thinking about that. For Web Audio 2.0, we really need a standard for doing this with everybody using the same API. Okay, so sorry, maybe a bit late. Finished.
You're just going to give me the opportunity to do
Yeah, okay. Yes. Okay.
All right, well now you all have a choice, right? It's 12:30. Do you want to ask a couple of questions or do you want to run off to lunch? Look into your hearts.
There is an hour and a half for lunch.
Oh, there's plenty of time for lunch. Well, then let's have a couple of questions.
So when you were measuring, is this on? Yes. So you've got the speaker simulation, and it's compressing the air inside the cabinet, but it also has an electrical effect because you have a back EMF into the amplifier. Did you take that into account?
Yeah, okay. So the different modules of the amp, we created them separately and then connected them. In a real amp, you've got interactions between these modules. In particular, between the power amp and the speakers. Okay, Jérôme Lebrun, the co-author of the paper, is the specialist here, but you've got to take into account the impedance of the speakers and the way it interacts with the power amp. So this part, we could not do this. To take this into account, you must either use tricks or do physical modeling. It's also the same with the preamp tubes. Sometimes there are some overload effects, some feedback effects where the current is coming back from one tube to the, and slowing down what is coming from the previous tube. So this part I started using some tricks I found that other people used, is that reshaping the transfer function depending on the envelope, with an envelope follower. So I started to do that. I can show you some things I started to do. And like this, when you play slowly, you will have a more linear curve and so on. But it works pretty well right now. And we made many blind tests, and the results were very good. People rated this second compared to 400 native applications in terms of sound quality and dynamics and comfort and so on. And I didn't pay them.
Who is your best favorite guitar player or band or musician?
Okay, I've got many. So, so it depends on the period. I started with the punk rock band and I didn't know how to play. Then I came back to AC/DC, Jimi Hendrix, Led Zeppelin. It's mainly classic rock, except Van Halen that I really like, but I will never be able to play like him. I prefer the warm sound than the cold sound from modern metal. Yeah.
Hi. So you mentioned transpiling the tone stack functions from C++ code. Have you any experience using WebAssembly with that, and have you found any performance impact?
No, to tell you the truth, we are waiting for the audio worklet to try again what we did, and maybe give a look at WebAssembly. But I haven't touched WebAssembly yet.
All right. Oh.
Just wonder how many lines of code?
5,000? I don't know exactly. It's a 2.5 year work. Yeah. And well, I'd like to put emphasis on the latency problem for people. I already talked with Paul Adno, Hongchen, and Raymond Toy from Chrome, but this is really a problem. When I play with Logic Audio, I've got a 64 sample buffer when I play my guitar or when I record. Here I've got 512. So.
Okay, one last question, and then do you want me to hand it off to you after that?
Show a map, that's all.
Okay.
Yeah.
Okay.
I'm just wondering if you did any testing, non-human testing. So like, for example, the partials that for the wave shapers like are matching an amp, and like
yes,
or the tone stack specifically, and if so,
yes.
your methodology for that.
Okay, so I cannot put it down. Yes, what we did is that we probe the signal on the different parts. So in the version with the analyzers, you can send a sinusoid input, and you can say at different stages what harmonics are generated, what is the frequency response, what is the waveform, and so on. Also, I put a mic in front of my amp, I sense the sinusoid wave in it, and I just, the microphone input was coming here with the same frequency analyzers I've got in the amp. And I try to match that for the different type of sounds. And finally, I used LT-Spice, a free version of the electronic simulator, electronic schema simulator, where you can send input waves, and you can probe the signal at different points. So, and there is a software called the Tone Stack Simulator that is linked in the slides and also in the paper. Then you can choose your amp model, you can choose the values, the tone stack, and even adapt the values, and you can see the curves. So yes, we did all of this. But in the end, as the real tone stack was not, it was not possible to emulate it, we did a lot of tuning by here also. And just an anecdote, I talked with Ivan Cohen from IRCAM, a guy who wrote a PhD about guitar amp simulations. And he was surprised by the quality of the sound here. And he said, well, Michel, you spent 200 hours maybe with guitar in hands, playing with friends and so on. But I had to write papers for the thesis. So I could not spend as much time as you did just tuning the sound. And it's also a matter of time spent with the guitar. But real people who write native applications, they also spend a lot of time tuning after they had the modelization.
All right, let's give him one big round. Hopefully people from Queen Mary will be guiding folks to lunch, but just to give you some kind of idea, we are, oh look, nice blue dot, we're about here, and if you can follow my arrow, this is going across the little lawn, and we walk past the old building, and that's annoying, and this building is where we're heading, called the Curve. You see it's got a curve on it. That's where lunch is served. The voucher you've got is for £6. That should normally be enough, but you can always add a little bit if you need to. You won't get any change, but you can add or barter with somebody maybe. I hope that's clear. Basically, we're just going in that kind of direction. This area here, you'll know you're in the right kind of space. This area here is a cemetery. Queen Mary has a cemetery on campus. We can explain another time to you what that's all about.
I don't know how to turn this off.
My responsibility. I think maybe that's...